Right, good morning, everybody. Can we settle down, please? Welcome to day 2 of the Kids Conference. And since it's a captive audience, this is now your infomercial. Give you an introduction to the Geological Society of South Africa. Many of you do know it, many of you are already members, but in case you're not, this is one of the reasons for belonging to the GSSA. We have a number of benefits, looking at a professional code of ethics, continuing professional development, things like the course that you are now, and various other courses that we have during the year. All count towards CPD, whether you do your CPD with the GSSA or with SACNASP or with various other professional organizations. We have a number of branches and divisions spread throughout the country, so you're likely to find something that is either local to you or the specific divisions to your interest. Specifically for students, the REI fund is something very useful because it can assist with financially towards conference attendance and mostly conference attendance. So students doing research can apply for additional funds for travel through the REI fund. On the more professional side, we are an RPO, recognized professional organization, with pretty much all of the stock exchange jurisdictions worldwide. So particularly if you are have acquired chartered status within the GSSA, you can use this to sign off competent persons reports with all of the international stock exchanges. Also for students, we provide a number of mentorship opportunities, both directly and also in coordination with SACNASP. Just to highlight some of the events, these are the ones that we have had already this year. And this is what we still have to go for the rest of the year. Please have a look at our website. You will find registration forms for all of these. And note that for pretty much all of our events, minus 1 or 2, we do provide a number of free student sponsorships. So again, on the website there are forms to fill in, and students, please take advantage of these. Next year is the 12th International Kimberley Conference in Yellowknife, assuming it hasn't burnt down by then. JOC has a number of flyers associated with the conference. They are in the exhibition room. Please go past and pick them up. Then in 2025, it is the 100th year anniversary of the discovery of diamonds along the west coast. And so the GSSA is putting on a fairly big event, technical sessions, as well as a big field trip. I invite you all to keep this in mind. There is a web page on the GSSA website with information regarding that, and as we get more and more planning done, that information goes on there. And I'd like to invite all of you to this event, held in Van Rensdorp and Port Nolloth, the exciting hotspots of the world. Let's see. I'd like to make a very big thank you to our sponsors, without which this conference would not have been able to take place. Please, guys, there is the exhibition hall just along the passage. Please make a point of going there. These guys have put on a big effort to not only provide sponsorship, but also to show you what it is that they're doing. So please go there, tea time, lunchtime, and directly after the session, you will not be allowed to go to the Digger's Braai unless you have passed through the exhibition centre. And no beers until you can prove that you were there. There are CPD credits available for this event. If you're doing it through the GSSA system, 16 CPD credits for the technical sessions and 8 for each field trip under formal learning, and 2 credits for SACNASP if you're doing it under that platform. Also, there will be a link to the recording made available to all attendees. It will be available on the GSSA YouTube channel. It will take a week or so before it gets there, so do be patient, but you will receive a link. You will also receive a link to the PDF of all the presentations that have been given. Again, this will all take a bit of time, but you will get it. So our session today, we start off looking at the Kohinoor and the Golconda diamonds, something that Ray spoke to us briefly about yesterday, and Hera is going to talk to us in more detail about it. Then we look at a couple of alluvial deposits, the second of our panel discussion, and then we move on into the Kimberley session, here and also after tea, after lunch. It should be a very exciting session in all. And so that is me, no more speech from me. And it remains now for me to introduce to you Hero Kalra, who will be presenting the next presentation. Hero is a senior research fellow at the CSIR in India. He's doing his PhD through the Department of Geology at the Pune University in India. And he's talking to us on tracing the mantle sources of Kohinoor and other Golconda diamonds. Hero, we look forward to your presentation.
Myself, Hero Kalra, currently pursuing PhD from the Department of Geology, Pune University, India. I specialize in geochemistry and diamond potential of southern Indian kimberlites. Today, I'll be speaking on tracing the primary sources of Kohinoor and other Golconda diamonds. These are the famous Golconda diamonds. The Kohinoor, which is a clipper type diamond, clipper stands for cullinan-like, inclusion poor, pure and reabsorbed. It is a colorless type 2A diamond, which was weighing 793 carats in rough and 105.6 carats after polish, currently in the Tower of London, England. The Hope diamond, which is a blue type 2B diamond, is 45.52 carats in the National Museum of History, Washington. The Ryainoor, which is a pale pink type 2A diamond, is 182 carats in the Central Bank of Iran. Dresden green, which is a green type 2A diamond, is 41 carats in Saxony. Moon of Baroda and Florentine are yellow colored diamonds. Jacob diamond, also known as Nizam's diamond, is 184.75 carats, larger in size than the Kohinoor diamond, is currently in the Reserve Bank of India vaults, Mumbai. Regent diamond, also known as the pit, is pale blue in color, type 2A diamond, weighing 140.64 carats in the Louvre Museum in France. Significance of Golconda diamonds. They are very well recognized for their rare colors, large carat sizes, and paucity of nitrogen atoms. Majority of them are type 2A diamonds. These renowned Golconda diamonds were recovered from Krishna River gravels. Southern Indian cretins always possess a rich diamond heritage and are target for diamond exploration. However, a promising deposit that was a source for Golconda diamonds could not be traced. Correctly identifying the primary sources of such large, dominantly type 2A diamonds, that is clippers, is crucial for understanding their origin, nature, and timing of magmatism. This is also essential from economic and geological perspectives. Similar case studies around the world. Large alluvial deposits greater than 100 million carats were mined in Ghana, Aquatia, and Ivory Coast. These Birmian diamond placers have major contributions from early Proterozoic kimberlites associated with Ebonian orogeny. Similarly, large alluvial deposits mined in Kalimantan on the island of Borneo had no traces of kimberlites or lamproites in the vicinity, and absence of kimberlite indicator minerals. Several models were proposed for their origin and transport of these placers. Keter proposed a kimberlitic origin for these diamonds. Alluvial deposits which could not be traced to a primary host rock also occurred in orogenic belt near Copeton in New South Wales. Davis and Barron proposed a volcanic origin for these diamonds. The major contributions to South African marine placers like Namaqualand and Namibia placers were the primary cratonic orangites, contributions from the underlying Karoo sediments such as Dwaika shales, Garip and Nama group of rocks which were transported by Paleo-Karoo and Orange rivers. So it seems to be a common but significant question. What is the source for these alluvial diamonds? Where do the kimberlites and lamproites lie? Besides, what was the mechanism for their transport? The Dharwar Craton. As most of the ancient diamond mines in India lie in the Dharwar Craton, we'll be studying its geographical extent and geological setting. The Dharwar Craton in the north The Dharwar Craton in the north is bound by Deccan traps. It is underlain by Kaladgi and Bhima basins, and it contains the Khadappa basin in the east, covering a total area of 4.5 lakh square kilometers. In the northeast, it is bound by Karimnagar granulite belt, and the southern granulite zone extends up to Palghat Kaveri shear zone. The Dharwar Craton was part of the Archean supercontinent UR and formed during Kenoran orogeny. These are supracrustal rocks consisting of north-south trending greenstone belts which are underlain by basement gneiss and tonalite trongemite granodiorites. They show progressive regional metamorphism from north to south with green schist species in the north and granulite species in the south. Craton was initially divided into western and eastern Dharwar. They show considerable differences in lithologies and ages. This is the Vajrakarur kimberlite field. As you can see, the Pennar River which traverses through the Vajrakarur field. There are conjugate faults showing a trend of north-northwest, south-southeast. They possess weak zones for kimberlite emplacement. The red symbols are archetypal kimberlites, while the blue ones are transitional kimberlites. Techniques used in the study. We have studied the kimberlite indicator minerals such as garnet, spinel, ilmenite, chrome dioxide, using whole rock major elements and selected trace elements to assess the diamond potential, finding the pressure and temperature estimates and depth of origin of kimberlites utilizing G9, G10, and G11 garnets, micro-diamond analysis performed on the root zone samples for assessing their diamond incidence and diamond potential, GIS tools and remote sensing imagery used to identify and study the geomorphology and drainage pattern of the area, Landsat optical imagery, digital elevation map using Astra 30-meter data, LIS-3 and NDVSI, accompanied with profile curvature and planar curvature to study the paleo channel. After 40 years of exhaustive exploration by Geological Survey of India, De Beers and Rio Tinto, more than 50 kimberlite pipes were identified in the Vajrakarur kimberlite field, which consists of Vajrakarur, Chikicharla, Kalyandurg, Timasamudram and Guti cluster. The Narayanpet field, which is in the north, consists of Narayanpet, Madhur, Kotakonda and Bhima cluster. The Tungabhadra field, which is consisting of Mantralayam, Chagapuram and Siddhanpalli, Raichur kimberlite field. Out of this, Vajrakarur is mostly diamondiferous. Narayanpet kimberlites are non-diamondiferous. A few contain micro diamonds. The rest, two, Tungabhadra and Raichur, are non-diamondiferous. The lamproites in the southern Indian diamond province, Krishna lamproites, which is a northern tip of Kadapa basin, the Ramadugu lamproites, Chelama lamproites, and Galedine lamproites. The Kadapa basin is an intracratonic basinal sequence. It developed by formation of different subbasins at different time ranges. The intrabasinal lamproites are emplaced at 1.4 GA. The Kurnool and Palnat subbasins developed as half grabens having an eastern tectonic margin and western transgressive margin. Kurnool is dated to be 1181 plus or minus 29 million years based on detrital zircon age. The fault leading to closure of the Kurnool basin, known as Rudavaram fault, correlates with the Pan-African events. The Atmakur fault separates Kurnool from Sirisalam, and the Ganikalva and Kona faults bound the Nandayal depression. This is the lithological map of the Kadapa basin. The key map shows state of Andhra Pradesh, where we can see towns of Kadapa, Vijayawada, the Pennar river which flows towards the east, and the Krishna with confluence of Tungabhadra flows towards Vijayawada town. There are many locations of placer deposits between both the rivers. The Kurnool basin consists of alluvial placers and Palnad consists of alluvial long transported diamond placer deposits. The Kurnool has a lowermost horizon of diamondiferous conglomerates. Ancient diamond mining in India. The ancient diamond mining was restricted to placer deposits along the course of rivers. There were 38 diamond mines, out of which 23 were located in the kingdom of Golconda. Diamonds were recovered along a 300-kilometer patch from the confluence of Tungabhadra and Krishna up to Vijayawada town. Paleoplacers were found in compact and hardened sediments such as Baganpale conglomerates. And recent placers occurred as alluvial and river gravels. The placer deposits estimated to have produced 12 million carats along with legendary Golconda diamonds. Mining was carried out extensively in a narrow belt on the right bank of the river from Kulluru through Pulichantla up to north until the river swings right through the meandering. This mine was set up in the 16th century and produced many of the Golconda diamonds, including the Kohinoor. Mining was conducted by gravel pitting. The diamond horizons in the gravels were narrow, less than 1 meter thick, 1500 meter long, and 500 to 800 meter wide. Large diamonds were recovered nearer to the river channel and smaller sizes reduced after the meandering. These are the ancient diamond mines which operated in the 16th century. The Irigodi Pamse, which is known as Gandikota. The mine di Kulure, which is the famous Kulur mine. the Kodavalikal, the Rawalkonda, and which is today known as Ramalkota, the Jonagiri, which is known as Jonagiri, and the Kurure, which is known as Vajrakarur. Both the rivers flow towards the east, and there are many ancient diamond mines located between both the rivers. The red symbols show kimberlitic pipes, and the green ones are lamproites. This is the Vajrakarur kimberlite field. This is Narayanpet, Raichur, and Tungabhadra. We have assessed the diamond potential of all the kimberlites and lamproites located in the eastern Dharwar Craton. Kimberlite indicator minerals not only tell us about the geochemistry of the host rock, but also about the mantle source. Higher percentage of chrome diopside showing larger Cr2O3 percentage. Greater derivation from garnet peridotite zone. Ilmenite showing greater than 50% of preservation potential for Vajrakarur kimberlites. The blue diamond represents the Vajrakarur kimberlites, while the open circle represents the Narayanpet kimberlites. The three diagrams here represent spinels as indicator minerals, which show higher percentage of magnesiochromite spinels from Vajrakarur kimberlite field. The garnets G9 and G10 show higher percentage from the Vajrakarur kimberlite field compared to the Narayanpet. We have used thermobarometry after Aschip-Cove, Kennel's empirical thermobarometer, and Sodhol's empirical thermobarometer. All the three thermobarometers show a deeper depth of Vajrakarur kimberlite field. Aschip-Cove shows a little overestimation of temperatures, while Sodhol shows a near correct estimation, correlates to a depth of 200 kilometers. We have used the graphite diamond transition of date 2012 and continental geotherms of Pollack and Champman 1977. Trace element diagrams for diamond prospectivity. HF and ZR show a lower content along with TI, which is character of a prospective kimberlite. The P5 kimberlite over here shows higher content of HF, ZR, and TI, which is non-prospective in nature. These both are Vajrakarur kimberlites. This is Narayanpet and Raichur. If you can see, all the kimberlites follow a higher HF, ZR, and TI trend, which is a non-prospective kimberlite. The ones on top show low HF, ZR, and low TI content. The P1 pipe, which is known to produce a 1300 carat single piece stone, shows a low RB and CS as well. The TI shows 80% accuracy for prospectivity, and when used in combination with CR and NI shows 89% of accuracy. Using the diagram, TI by NI versus CR by Y negates any uncertainties related to metasomatism, post-magmatic alteration, and calcium retention. If you can see the fields, the blue color field shows the prospective kimberlites. All the Vajrakarur kimberlites fall in this blue colored field, while the black color region shows non-prospective. All NKF kimberlites fall in this. Inferences from kimberlite indicator minerals. The compositions of kimberlite indicator minerals from Vajrakarur indicate a greater control of residual garnet in source regions, high magnesiochromite content, and their derivation from a diamond stability field. The indicator mineral compositions, thermobarometry, and trace element diagrams show poorly to non-diamondiferous nature of NKF kimberlites and show their shallow mantle source regions. NKF kimberlites also show a higher ilmenite percentage, showing higher oxidation potential responsible for poor diamond preservation. From the kimberlite indicator minerals, it can be deduced that strong diamondiferous roots were present below the WKF mantle, which was a prerequisite for their diamond potential. Previous studies also presented WKF as a major deposit and discussed their diamond poor nature of NKF, but did not comment on their link with Golconda diamonds. Microdiamond analysis. Geological Survey of India carried out exploration by drilling, pitting, and testing of bulk samples from 13 kimberlite pipes from Narayanpet kimberlite field. 110 tons of hard bank and soft weathered kimberlite from Raichur, but did not yield any macro diamonds. Only micro diamonds were recovered from NKF by De Beers and Rio Tinto. Micro diamonds have also been recovered from Tungabhadra and Raichur kimberlite field. GSI also carried a preliminary investigation for placer diamonds in Raichur district, covering an area of 200 square kilometers from Bhima and Krishna river basins, but failed to locate any placer diamonds and indicator minerals. Diamond concentration for WKF pipes is 65 carat per 100 ton for TK4. P7 yields 44.49 carat per 100 ton in overburden and 7.9 carat per 100 ton in kimberlite pipe. Gem quality diamonds weighing a total of 16.3 carats recovered from CC4. Individual weight is 3.55 carat. CC5, which is 1.28. P2 is 1.56 and P10 is 1 carat, which could be more potential sources in terms of diamond recovery. All the pipes from Vajrakarur were diamondiferous except the P5 pipe. WKF most prominent in regards to diamond potential compared to other kimberlite fields, although they show less individual sizes and quantity. The micro diamond incidence correlates well with the kimberlite indicator mineral data, depth by thermobarometry and trace element data. Current figures for diamond concentrations are lower concentrations of original values. These are the lamproites, 4 lamproitic fields which occur in the Kadapa basin. The white region shows prospective lamproites, while the dark area shows non-prospective. The Chelima field shows a trend which is poorly diamondiferous to prospective. All other 3, Garledine, Krishna and Ramadugu, show non-diamondiferous nature as they follow the black trend behind. So we talk about the retained placers in intracratonic basins, that's Baganpalli conglomerates. Diamond-bearing Baganpalli conglomerates is the lowermost formation of the Kurnul group. It's exposed on the western margin of the Kadapa basin. The basal conglomerate of this formation is diamondiferous, 5 centimeter to 1.5 meter thick, and average of 30 to 40 centimeters. Conglomerate beds occur in the form of channel lags at Ramalkota, Baganpalle, and Munimadugu. Diamonds are mostly part of the matrix. They are essentially, these conglomerates are composed of quartz and 95% of chert as framework grains, and they are oligomictic in nature. Diamonds are part of the matrix. The composition of framework grains indicates provenance as continental block and stable craton derived into a passive oceanic setting. Mesoproterozoic kimberlites, which are at the western margin of the Kadapa basin, were assumed to be the source until Joy et al. 2012 showed lamproites, which were intrabasinal lamproites like Chelema, to be the primary source of the Baganpalli conglomerates. The morphology of diamonds and absence of any wear features or marks or percussion marks indicates they were not transported over long distances, and they are characterized as alluvial deposits. The Krishna River gravels, transient placers occur all along the Krishna River. They occur on the terraces and were mined before primary deposits were located in India. In the eastern tip of Kadapa basin, when the Krishna River takes a meander and southerly path, only smaller size of diamonds recovered after the meandering. A similar phenomena of hydraulic sorting was seen as size of diamonds decrease away from the channel. Often larger diamonds were associated with coarser gravels. Tectonic upliftment causing river rejuvenation, cutting of neoproterozoic fold belts leading to transient placers. Larger gravels in the Palnat basin conglomerates acted as trap sites for diamond placers. The presence of attrition features denoted by crescent-shaped marks or percussion marks are common in these Krishna rivers placer deposits. The feature of these diamonds shows long transportation, which is not observed in the conglomerates from Kurnul subbasin. Hence, 2 populations of diamonds exist in the EDC. Diamonds in the hardened Baganpalli conglomerates of Kurnul subbasin and diamonds that have undergone a long history of transportation represented by alluvial and quaternary placers. It is only after the mid-Miocene the sea level regressed and riverine features, fluvial channels, channel lag and gravel deposits, river terraces and quaternary alluvium could develop. Paleochannel mapping. Similar paleochannel mapping study was carried out along the course of Saraswati River by Gupta, Bhadra and Sharma using wide field sensor, advanced wide field sensor, LIS-3 imagery. Precautions have been taken to avoid existing fluvial channels, canals and waterlogged areas while connecting two ephemeral drainage patterns. A paleochannel usually shows a turquoise color in LIS-3, which is false colored composite imagery, and vegetation is in tones of red in NDVSI. For further confirmation of paleochannel, we use normalized difference vegetation seasonality index previously used by Oringo and Petre. Profile curvature and planar curvature were used to distinguish ridges, basins, and drainage divides. The highest elevation is 1078 meters and the lowest elevation is 9 meters. This is the digital elevation map. As you can see, the lowest elevation shows dispersal or spread of placer deposits in the Kurnool-Nandayal depression. These both faults act as a boundary fault for the Nandayal depression, and these are the alluvial deposits. This is the LIS-3 imagery. So we have tried to connect the channels. The turquoise and greenish colors are waterlogged areas, but show presence of the water content, which is this is the NDVSI image, which shows flow direction arrows. It shows the flow direction arrows point from higher elevation towards lower elevation, and our paleochannel flows, it follows the flow direction of the arrows. This is the profile curvature. If you can see, the negative values show convex upward shape, and this negative value is denoted by the green color. There are presence of green color ridges in the middle, which act as water divides or watersheds, and our paleochannel follows a parallel pattern towards this. This is a planar curvature. Again, these act as water divides. So the red color is represented over here, and they act as watersheds. This is the inset image of the flow direction arrows. So if you can see, all the flow direction arrows point towards the northeast, and our paleochannel connects one pattern to another drainage pattern. There are placer deposits also present in the paleochannel. Geodynamic events and implications. Formation of upwarping axis, which led to the north-south drainage divide. It can be correlated to the Deccan plume superswell. This was the cause of river rejuvenation and cutting of Neoproterozoic fold belts, leading to development of transient placers, continuous drop down in sea level during mid-Miocene, and its ultimate drop down during Pleistocene. Marine regression led to progradation of delta, formation of channel lag deposits, river gravels and quaternary alluvium. Denudation of preserved kimberlite species in the recent event led to liberation of heavy minerals and large diamond deposits away from the source, similar to the Guti cluster, which has been discovered in recent 2000s. The last slide, I have done some comparison of the Orange River with the Krishna River. The sequence of events have been arranged in the timeline. So if you can correlate, the Orange River starts with deposition of Lower Karoo, Oliphants and Namakwa land during Cretaceous and pre-Cretaceous. There's a southeastern uplift, which is tertiary. Upper Karoo River captured by Lower Kalahari River. Orange River transient placers near Hopetown, Douglas and Prisca section. Drop down in sea level during Middle Miocene, during the existing Paleocoa. Beach placers, extensive reworking during late Pliocene to Pleistocene during the existing Paleosac. Beach placers. Namibia and Namaqualand placer deposits, and lastly followed by Quaternary River gravels along the Orange River. The Krishna River of India, which has analogous events taken place, starting by Deccan Cretaceous uplift, rejuvenation and cutting of Neoproterozoic fold belts at Palnat Basin, transportation of large-sized diamonds from WKF through Pennar River Paleo Channel, deposition of transient placers at Kulluru, Ustappale, Paritela and Chandralapadu, drop down in sea level during mid-Miocene, absence of any eastern shoreline placer deposits because of loss of sediments to offshore and lack of enrichment, poor reworking, quaternary river gravels deposited along Krishna River. Special thanks to Tanya Marshall and John Bristow for inviting me and giving me opportunity to present at the Kimberley International Diamond Symposia. Thank you for your attention.
Hero, thank you very much for that. Don't disappear. Don't disappear. Come. You still got to answer questions. That was a really interesting presentation. Thank you very much. I have seen many of those gravels, and this was really interesting to hear more about them. Do we have any questions from the audience? John.
You hear me? Hero, thanks. That was fantastic. And I just want to make a couple of points to all of the diamond geologists in this room, particularly the alluvial geologists. Where's Lyndon? And, you haven't seen it all until you've worked in India. And I think some of you here, where's Stuart? Stuart, are you here? We worked in Antwerp. And I think John Ward, I don't know if he's here, but the other people who have worked in India. But it is just the most amazing place. And those alluvial deposits, and you saw that map of Calrose, or Hero, that map, all our diggers, these guys had done it before. You saw that map with hundreds of localities.
We can put it again, no problem.
Yeah. It doesn't matter, but I mean, that's we've seen it in the good times. Sinazo's work showed or Sinazo and the girl before who did the study showed about 2,000 small operators in this country. The map that James showed with this horrible plunge of the loss of the small diamond diggers. And it just shows, that alluvials are important. But those of you, as I say, who haven't been to India, haven't seen these places, go and walk the Krishna River and live amongst those people. Ask Stuart, it's just the most amazing place. And I've been very fortunate to see those areas. And it's great that you came here and gave this presentation. And anyone who wants to learn more about diamond geology, go and speak to Hero and read the literature. There's an amazing amount of literature. And it goes back hundreds of years. I think for many of you who don't know the history of diamonds, and it came up several times yesterday, this is an old industry, 2,000 years old. And that's how long it's been going. It's extremely resilient. Paul Zimnisky made that point several times yesterday. But do yourself a favor. My recommendation, go and spend some time in India. Thanks.
Thank you, sir.
Do we have any questions from anybody else? Lyndon?
Thanks, Tanya. Yeah, fantastic presentation. Thank you very much. And it's nice to see the comparison with the Orange River, because there's not many systems like that, the diamondiferous systems in the world, that actually carries diamonds over such a long distance. Just a question with us in the Orange River, especially the middle Orange River. our deposits only started to develop once we've cut down right to the bottom of the Dwika and started to get clasts out that can actually keep the diamonds back. What is the source of the clasts in your rivers?
Yeah, you can see this Penna River. It is traversing across many kimberlites in the Vajrakarur kimberlite field. And after this river comes towards the middle, there is a mine which is known as Irigodi Pamse, today known as Gandikota. It operated in 16th century. So these result in placer deposits, the erosion and denudation of these kimberlites.
Okay, but the clasts in the river, the pebbles and the boulders, where is that from? What was it eroded from?
The gravels are mostly conglomeratic and they act as trap sites. We find larger diamonds in coarser river gravels.
John might want to comment.
Yeah, go.
Thanks. Yeah, I've been very fortunate to be able to see both the Banganapali conglomerates and also the Krishna River. Lyndon, the gravels come from that eastern belt, the fold belt that comes onto it. That gives us the gravels in the Krishna River looks just like the orange. I have to tell you. So the gravels themselves, not conglomerates, the gravels are derived from that metamorphic belt on the East Kurapa Basin. Yeah.
Yeah, Lyndon, it's an important point that you make, and in my impression of those deposits, also having walked a lot of them as John has, that the grades are probably lower, that the diamonds are bigger in general, and it's exactly the argument you were talking about yesterday, John. But yeah. Yeah.
The two deposits I showed, two basins. Yeah, I'll just show again. Yeah, so these are the two basins. This is the alluvial deposit which is in situ. Okay, yeah, the source is very near to the west, and intrabasinal source, one lamprowite field. So this is like alluvial deposits which show short transportation, and these ones are long transported alluvial deposits. Yeah.
And then it again highlights the importance of the Dwika. John might want to comment as well on our deposits. You know, those Dwika deposits and the big boulders make a huge difference. And the last thing, again, too, it is, you know, hundreds or thousands of very low-grade kimberlites. And our steward of MSA at that time, and ourselves and others, we did a lot of work there. There are many, many, many kimberlites. In that case, old kimberlites, mostly Proterozoic, and they've all got a sniff of grade. But, you know, De Beers have worked there, Rio have worked there. There's never been, you know, a great dripping roast of a diamondiferous kimberlite. Very much the same as, you know, tapping all of these hundreds of kimberlites around Kimberley with low grades. Lyndon. A lot. Yeah, they're all down at root zones. Yeah. No, well, you see again, Lyndon, it's the big difference there again, and I see Jürgen is here. You might want to comment. He's probably been there. You know, the Bay of Bengal never had that same history of, you know, West Coast diamond deposits are there because of the weather, in simple terms. Yeah, they're buried. They just dispersed.
They were lost offshore.
Yeah, but they've never been concentrated like our amazing West Coast.
There were no energy conditions for reworking and enrichment of the shore deposits, like they were over here in the western shore of South Africa. Yeah.
No, it's a fascinating deposit, so we're going to organize another trip. He's going to show us around, so put up your hands. Yeah. Yeah.
Pleasure.
Thanks.
Yeah.
Thanks very much, Hero.
Our next presentation is by Gary Dawkin. And Gary started life off as a geologist in 2011 along the Middle Orange River with Rockwell Diamonds, where he progressed to regional geologist and then exploration manager. Then he did a stint as a contract geologist to Petra and Botswana Diamonds. And then since 2018, he's been working in Angola as an expat senior exploration and production geologist for the Lulo mine with Lucapa Diamonds. And he's going to talk to us about the deposits there. Gary?
All right. Okay, good morning, ladies and gentlemen. Yeah, thank you, Tanya, for the introduction. Today I'm going to be talking to you about the unique alluvial gravel deposits of the Lulo mine situated in Angola. All right. Okay, just a few of the table contents we're going to go through. We're going to have a look at the location, the Coquila River settings, the gravel deposits and characteristics, such as the terrace gravels, the Lazeria or floodplain gravels, our large stone distributions, another comment to be discussed, and some exploration for the primary sources and the Kimberley bulk sampling program. Okay, Lulo lies in Angola's diamond heartland of Luanda North, about 630 kilometers from the capital Luanda, and about 170 kilometers west of Sarimo. We have a big concession, 3,000 square kilometers. It's one of the world's most prolific alluvial diamond fields, producing regular, high-value Type 2A diamonds. Commercial productions of alluvial mine started in 2015 through the company SML, partnership with Lucapa Diamonds, our Angola's Indiama, and our private partners there. So alluvial mining at Lulo focuses on the floodplains, the Lazeria deposits, terrace deposits along a 50-kilometer stretch of the Coquila River, which runs through the concession. Okay, so the Coquila River is a first-order tributary of the much larger Kwango River. The Kwango River gives rise in the Kalahari sands and upper Cretaceous sediments before it reaches the sandstones and shells of the Karoo supergroup in the Kasanje Basin, depression to the north-central, northwestern Angola, where Lulo is situated. This is our concession with our Coquila River on this side and our Lulo River on the north. This all flows out into the Kwango Basin and north out through DRC. Okay, the Coquila River setting. So being the first order tributary of the Kwango River, the Coquila has a small catchment area of about 1,900 square kilometers, but it's very unique in that the Coquila is a small-scale, gravel-starved system. Today's energy is insignificant and was similarly inconsistent throughout the Quaternary due to climatic changes. Important to note, the bedrock of the Coquila system is soft shales, mudstones, sandstones of the Kasanje group, equivalent to the Beaufort group of the Karoo supergroup. And of course that it's a producer of large Type 2A diamonds. The largest Type 2A being a 404 carat diamond recovered in 2016, and to date we have found 37 plus 100 carat diamonds. Looking at the fluvial environment in the Coquila Valley, it comprises of terraces, which represent the ancient river courses, Lazerias that are the much younger floodplain deposits, and the main river channel that is currently active. The terraces step down towards the present Coquila like a staircase, and the Lazeria deposits are built up during lateral migration of the main channel, with the present Coquila marking the end of the channel's lateral journey. Just looking at our Google Earth images, we can see our terrace deposits on the side of the Coquila River, with our Lazeria floodplain deposits there, and the old fossilized channels running over the top of it. Okay, just looking into the terrace deposits a little more. This is a west to east cross-section of the terraces as they step down towards the current Coquila River. You can see the very gradual bedrock elevation drop there, with a big incised event for the Lazeria deposits being formed. So all of the terrace gravels as well as the Lazeria gravels contain diamonds, while the Coquila River itself has been examined and does not contain gravel or diamonds. We have found some hand axes within our gravels representing a Quaternary age, but they haven't been dated as of yet. Okay, looking at the Lazeria model. The Lazeria model represents a down-cutting event. The bedrock is some 8 meters below the terrace bedrock elevations. This would have caused an incision to the new base level, and a braided river would have formed with our gravel and diamond input into the system. And once that base level had adjusted and alluviation, it would have stopped at its current meandering system. Okay. So being a gravel-starved, small-scale system, the gravel thickness rarely reaches 2 meters and is typically on average about 30 centimeters. Just to look at some of the stats, we've drilled about 37,000 auger holes at about some 300,000 meters, with our average gravel thickness about 0.24 meters. So very short on gravel. The terrace gravel deposits have a mixture of predominantly pebbles to cobbles size clasts. Boulders, and especially large boulders of greater than 5 meters, are very rare. All right. Yeah, so small boulders are more prevalent in our terrace gravels, while the Lazaria gravels tend to be more pebble cobble with some larger cobbles. Okay, the gravel of the Coquilo has some distinct characters. Firstly, the geology of the class comprised mainly silkrete and quartzites with minimal other rock types observed. And secondly, there's 2 class populations within the gravels, one being a well-rounded clast, with the others being sub-rounded to subangular. The well-rounded clasts population is not due to the Coquilo River, as the energy and transport distance is poor. Instead, the well-rounded class would have been sourced from a much older gravel sequence from an unknown source. And the other population is a sub-rounded to subangular silkrete gravel, which is most likely sourced from the Gresh polymorphs. Yeah, sorry, I just wanted to show just some pictures of the well-rounded clasts. And these are the boulders. This is probably about for 3 or 4 years worth of production. The smaller class there, and that's Mr. Spags with our very thin gravel deposits on that side. Okay, just moving on to the terrace gravel deposits and a little bit of an in-depth look into it. So the terrace gravels occur between 1 and 6 meters below the surface and are generally covered by weathered lateritic soil, sands, or clays, and they're found within about 2 kilometers from the current river. They're mostly matrix-supported gravels with sub-rounded to subangular clasts, for the terraces being a silt to clay-rich matrix, which obviously provides a processing challenge for us through the plant. The class makeup is about 95% silkrete with some quartzites. We have some rip-up bedrock class and a varying amount of kimberlite indicator minerals that we see within. This is just an example of our gravels. We can see our bedrock rip-up class, a little GPS for scale. And this would be some of our terrace gravels, about 30 centimeters with overburden of sand and clay, undulating gravels there. Just some of the exploration statistics for it. Our grades for our terrace deposits range between 1 and 6 carats per 100 cubic meters. On average, we're about 5.5. Our stone size to date, or end of 2022, is 1.38 carats per stone. We have some some trap sites. We have some bedrock undulations and some boulder trap sites, and that's about it. Just an example below, we have a little bedrock undulation. This one, unfortunately, was with flow. Didn't attribute to our deposit, and another just the example of the thin gravels we've seen. All right, just to mention some of the most prolific mining blocks we've encountered to date. Block 8, this is where the 404 carat was uncovered, and this has been attributed to a meander channel bend with a narrow feeder channel, which would have had higher velocities and transport of the bed load, and then opening into meander bend and depositing of that. To date, we've uncovered 8 plus 100 carat diamonds from this area. In block 46 on the side here, this is a representative of that area. We've also covered another 8 plus 100 carats stones from there to date. That's attributed to the bedrock undulations we've seen within that. Okay, moving on to the Lazaria deposits. Okay, so the Lazaria gravels would occur between 6 and 12 meters below the surface and represent a nice upward fining sequence with basal lag gravel, fluvial sands, silts, and clays above it. You can see a nice represent here, our bedrock, crude bedrock, gravel interbedded, sand and clays above. They are close to the river, about 300 meters there. Most of them is matrix to class supported gravels with the same sub-rounded subangular clasts. There's tend to be more sand to silt matrix rich, and they are of the same class makeup, 95% silcretes, quartzite, rip-up class, and varying amounts of the kimberlite indicator minerals. If you look to the bottom here, you can see the amount of ilmenites that we find within the gravels, making up a large contribution. Just some of the production stats we've seen to date. The grades range between 4 to above 16 carats per 100 cubic meters. On average, we're about 10.5 carats per 100 cubes. Stone size slightly coarser than the terraces at 1.4. Some of the trap sites we've seen within the Liz areas are some inside channels within the bedrock, some coarser cobble bars, and then some 90-degree turns in the major river course. You can see an example of the basal gravel lag here. Just to note in this picture, you can see this is the current Coquila River. You can see there's no gravel or anything contained within it, and we are mining the basal gravels well below on that side. One of the blocks to mention was block 19. We found 6 plus 100 carats there, one of them being that 170 carat Lula Rose pink-orange diamond. All right, moving on, just to have a look at some of the trap sites we've seen in the Liz area. As you can see here, this is the Liz area river course with some sharp 90-degree turns in there, obviously due to some tectonic activities. When plotting our gravel thickness maps, we can see the formation of the gravel thickness on the inside of the turns, and after production, we've correlated that with our large stone recoveries in these gravel bar developments. All right. Okay, just what we're looking at here is our large stone distribution plots, and these are one of the tools we've used for further exploration and planning for both our alluvial and our primary source activities. What is plotted here is every stone above 10.8 carats recovered from all our mining and sampling programs throughout the Coquila, and it tells an interesting story as we go forwards. This is plotting everything from 10 to above 100 carat diamonds. As we look at the next slide, we can see the green stones, which are 25 carats and above. There's a really equal distribution across all our sampling areas, central, north, and south. As we start removing the finer stones and now looking at just the 45 carat stones, there seems to be a small trend that we can see, like that there's more concentration to the center, a slight decrease to the north, and a concentration to the south. Now looking at just our orange stones, our plus 75 carat stones, we can see a definite stop in our large stone distribution downstream, indicating most of the concentration to the center and upstream. This is then mirrored again with our plus 100 carat diamonds on that side, where there's a definite cutoff around block 4 and then everything up to the south. Just something to note, this technique was used to find block 46, where we recovered the 8 plus 100 carat diamonds within a 7-month period. All right. So this unique project in Angola has yielded some spectacular recoveries over the years, with consistent production of high-value diamonds, rivaling that of the Middle Orange region. Some of the results speak for themselves. In our quarterly results here, we're seeing dollar per carat values of $3,000 to $4,000 per carat. Our final 2021 production years of $2,800 per carat, with 2022 at $2,400 per carat. Our half-year figures for 2023 sitting at $2,300 per carat. Just important to note, this is all done at a 1.5 millimeter bottom cutoff. Okay, moving on to our exploration for our primary sources. The primary sources of the large high-value alluvial diamonds mined at Lula has not been discovered. More than 560 geophysical anomalies have been identified, most of which have proven to be kimberlitic when drilled, making the concession a very prospective area. The exploration program is significantly advanced, and in 2022, a kimberlite bulk sampling plant was constructed at Lula to expedite the kimberlite exploration program. Thank you, Council Met. On a concession with such a high anomaly to kimberlite conversion rates, it is expected that new kimberlite discoveries will be added to the priority sampling list as concurrent discovery drilling and min-chem analysis continues. All right, and just looking at some of our kimberlite bulk sampling results, obviously with the coarse size distribution of the alluvial deposits, it's warranted a slightly different approach to the kimberlite sampling program, with an increased bulk sampling size to give adequate chance for our recovery out of the kimberlites. Majority of the exploration program is all upstream of where we've uncovered our large exceptional diamonds, and as well as being based on exploration results and other considerations, including expert peer review. The most significant results to date is from Kimberlite 164, where a total of 64 diamonds totaling 82.37 carats, with the largest stone being a 15.27 carat recovered. So the exploration for the primary source is firmly underway. All right, so thank you very much for listening to that. Just some special mentions to obviously Le Carper Diamonds for allowing me to present this work, and then obviously to Spags for the use of his illustrations and the groundwork for this presentation. All right, thank you very much.
Thanks, Gary. Go ahead.
Hi. 4 years ago, your top management were at the Mining Indaba in Cape Town, and they had two big messages. One, there were big changes coming in Angola in the regulation side, and two, they were that close to finding the primary source of your alluvial diamonds. Now, they got it right on the regulation changes on Angola, but 4 years later, you seem to be nowhere near this primary source. Can you tell me what you've been doing for the past 4 years and why it's so hard to find the source of these diamonds?
Yeah, you make some good points there. As I alluded to, obviously, we see the amount of kimberlites that we're finding there, anomalies to kimberlites and sampling programs there. So it's one of the few places that we've seen that has too many kimberlites to look at. So we're doing our best to try and narrow it down, and obviously knowing that we're looking for the type 2 bearing ones, that we're going to have to sample a little bit differently or do something else on the approach side to kind of pinpoint those big stone producing kimberlites. Yeah, we've been working as hard as we can, drilling as much as we can. That's what we've been up to.
Top management being a tad over-optimistic in their assessment?
I can't speak for their comments. I just do the work on the ground there. Yeah.
Okay, just a quick question for you. Is there presence of the calendar formation in your concession, and do you think it might be related to some of your findings?
Sorry, there's presence of
The calendar formation, the basal
Yeah.
conglomerates.
We haven't found any presence of the Calonda formation in our areas. I think there was a discussion earlier on. We've even looked at our gravels, and the Calonda is known to have some of the agate content within it, and we see very minimal, if not none, agates within our gravels. They're mostly just the silkretes from Gresh polymorph. Maybe there's some reworking, but it seems to be most in that area has been stripped away for that side. We have done some drilling further up to the north as well to look for any Calonda formation. Obviously, it will be very beneficial, but nothing has been found to date. All right.
Yeah, Gary, I think you've definitely got to go and stomp around India and get Kelra to take you to the Krishna River and look at those alluvials and the kimberlites. And I'm sure you've got it. Have you got size frequency plots of all these amazing diamond populations?
Yes.
And you're going to show them to us or not?
Not today.
No?
Not today.
But it'd be fascinating to compare them to the Orange River again, or the middle where you worked.
Yeah, no, we have all of that data, yes.
Okay.
Definitely compare. Next time.
Morning, Gary. Hans Hickstedt, Jean Bull Diamond Mines. I'd just like to find out, your exploration looks good on the alluvials. Do you have a systematic plan and a program that can give you a life of mine for alluvials, excluding your kimberlite you're looking for?
Yes, yeah. So we do extensive auger drilling as well as excavator pitting. The gravels that we see on Lula are very thin channelized features. So we had to refine our exploration techniques down to about a 10-meter drill spacings by 100 down to 20-meter line spacings on that side. Like I said, we've drilled 37,000 holes and about 300,000 meters since 2015. So it's one of our key drive on that. Once those gravels are identified, we do our bulk sampling, obviously to find out the gravel content, diamond content, and valuations for it to put forwards to our life of mine plan going forwards. Yeah.
All right, so life of mine is still in progress.
Yeah, it's continuously ongoing. Yeah. So we're looking at the upstream of the Kukwila, obviously following the trend of the large stones, to potentially find a point of a cutoff or if it extends further out of the concessions. And then plans are to also look on the Lula River into the north of the concession to obviously add life of mine to the project.
Sure. Thank you.
All right, thank you.
Morning, morning, Gary. Thanks, very great, nice presentation. Two questions. What is the total life of mine related to the right now, and what technology are you using to get the type 2s? How are you recovering them?
All right. So currently our life of mine sits at we have about 2.5 million cubes around. That gives us about, at current, three years worth of operation. Obviously, like I was alluding to earlier, we increase that with our drilling and concurrent exploration. So we'll do a revised review at the end of this year. For our large stone recovery, most of them have actually come out through the flow sort, but we do have XRT Tomra on our coarse side that has found some of the other type 2 stones.
Thanks.
Sure.
Sorry, I just want to go back to the exploration side where you're looking for kimberlite.
Sure.
So I saw just you put the geophysical data you have. I don't know if you are also doing some other technique like regolith mapping and geochemistry or soil sampling in those areas.
Yes, so we have done some soil sampling, and then obviously all the drill samples are taken off for geochemistry and analysis. We have Paul Allen heading our kimberlite department on site, looking at that, working with Richard Price from the Copper Diamonds to choose our most prominent samples.
Anybody else? Okay, Gary, thank you very, very much. We look forward to the next presentation to see all those SFDs and all the rest of it. Thank you. Right. More alluvials. Today we have Sarah Turnbull with us. Sarah is a senior exploration geologist at SRK Exploration Services with over 10 years experience and exposure to different geological terrains and commodities. And she's talking to us this morning about the burden of proof using the Save River Diamond Exploration Program in Mozambique, which is actually where I first met Sarah many years ago. Sarah, where are you? There you go. Forward, backward, and the...
Forward, backward, and there's the... Okay, thank you. We've gone from a giant to me, who is definitely not a giant. So my background, as Tanya read, is actually I'm an exploration geologist rather than an expert in diamonds like the rest of everybody here in this room. But when Tanya and John gave me a call to ask me to do a talk, you don't say no. So I'm here, and I'm really just here to discuss the process that we went through with regards to our alluvial project in Mozambique, and I suppose just a general exploration plan for most alluvials, and the recipe that we followed. So as an exploration geologist, we have a success rate of less than 1%. I actually looked at some of Rio Tinto's data, and they published their data at 0.03%. So we look at a number of projects and possibly are a bit cynical, but I'd also like to say we're realistic, and we look at projects and see how to progress them the best way possible protecting both the investor, the sort of all the players involved, and you really do have to look at all the possibilities. So at the first sort of step that you'd start with is really the ground selection, your target generation from then that work, your target testing, and then if you're lucky enough to go into deposit delineation and take it from there. So really just with the ground selection, just a bit of a background, there's so many books and so many journals and pieces of information that you can read, but really just looking at your tectonic settings and all additional references that can help you put into a place where your deposit can be preserved. I think that's also a large part that we forget, is that while it couldn't be there, has it been preserved over these years of time, because it's taken so long, and nature's pretty harsh. So, you know, have we been able to preserve that mineralization that we're interested in? So that's actually with primary and secondary. The secondary as well is just really your deposition, and then the concentration of potentially your better stones, because all your sort of junk has been crushed and deserved and destroyed, through the whole sedimentary process. And then really just going through good fundamental geological information that from historical reports and just evidence from geochemistry and any additional information that can help guide you on where you'd like to go. So with us and with the project that I worked on, the fundamental plausible geological model that we were going for is that, let's see, there was the Marangi fields and then Maroa over here, and that there were so many diamonds that were hopefully what our plausible geological model was, is that it then traveled down the Runde and the Save rivers on down to Mozambique. And with the change in gradient going from the high plateaus of Zim, then down into the lower gradients of Mozambique, the river would have lost its load, lost all of its, well, the majority of its heavies, and ideally if there's diamonds in the system, that's where your diamonds are going to concentrate. And so that's where we then started our project, and as Tanya said, both Tanya and John Bustow and Spags that Gary spoke about all visited at the deposit, so or area of interest, so that we could start up with our project. So, and as you can see, sort of this gradient from the 700 down to your 200 over there where the project was situated. So it was really an ideal location that we were looking at. So the targets that we then, so our second step, so we found a decent location, a great sort of mineral systems approach that we were looking at. That was really great. Now we were looking at the targets that we were going to then test and justify our targets that we were looking at. So we looked at a number of gravels, just like Gary alluded to. There was a number of terraces, and what we focused our attention on was really the Save Valley rather than the higher plateau area. While they didn't really have the classical attributes of what we were seeing in the Vaal and the Orange River terraces, there were additional sort of qualities and sedimentological qualities that could justify why we were targeting this region in specifics. So we then mapped a lot of kilometers in very hot Mozambique, in relatively dangerous areas where there were still mines in the ground. So we had to have locals with us to say where we could and couldn't walk. And what we then picked up was sort of on this plateau, we weren't interested at all in that area, and we excluded it. However, we focused our attentions on the 230s, the 230 meters above sea level gravels, and they had basically the best characteristics and trap sites that we were interested in testing. And this then warranted, and we were able to justify a bulk sampling event where we then went through to go and test all these different gravels that we were able to find through, as Gary said, through pitting with our excavators to then test were they feasible. So our target testing that we eventually did, we can see our gravels over there going down towards sort of a slump system. They were sitting on a hard calcrete layer, which was, it was really quite hard. And our gravels ranged between 3 to 5 meters in depth. And then their sort of thickness was also roughly maybe 50 centimeters, 50 to about a meter in thickness. We then had a total of 8 trial pits, which we kept separate after a lot of fighting between the production site and the geologist. They were kept separate so that we could then sort of track where we were finding diamonds versus barren gravels. There was only a single unit in this area that we were looking at, and we tested it through putting it through the barrel screen. From the barrel screen, it went into 2 16-foot rotary pans where we did a number of tests and QA/QCs where we had traces that we put in to make sure that we weren't losing potential diamonds through the system at all. To begin with, we had a jig system where it would classify the different sizes, and I spent a lot of time at the sorting tables looking at the concentrate to see what were we getting, what were the kimberlite indicator minerals that we were getting, were there anything of interest, were there any diamonds. Just really, as a summary of the project, we did find some diamonds. There was a total of 70, as you can see, at 43 carats that we recovered. But they just weren't feasible. We weren't able to sell the project. The company actually had another option to go in and start developing a ruby project high up north, and it wasn't feasible for us to go and have as many expats as we did running the project and doing it. So we did all the right things, but unfortunately, the statistics of the project in general just didn't allow us to move forward. And essentially, that was the burden of proof, is that there was just insufficient quality and quantity for us to move the project forward. So that was the long and the short of our project. I got to go there for a year and lived there and met really decent geologists. But in order for me to now continue for the rest of my time, I went and looked at a few more stats. And so what I was then looking at and what I was really interested in was the market that we would have been selling our stones to as a junior. We were looking at small stones and we were looking to sell that. And this is not a secret, it's everybody discussed it earlier, and really just how the market has changed. And it was hard enough for us as juniors in the beginning, but now the market as it is, it's even more difficult, even more tough for us as juniors to compete and to be involved in the market. So this is from the RAP reports, and essentially what they're saying and what they've just announced, I think it was on the 29th of July, they said that there's very little demand in the market that they're seeing currently in July for the under 3 carat stones, and that the synthetic stones are really the area that's damaging us as hard as it is. So again, from a junior's perspective, and sort of where my passion lies, it's a bit disheartening, and it's something that we definitely need to address and be aware of and start discussing and bringing more attention towards this sort of challenge that we're facing. Further on, I mean, again, this is something else that we looked at, but essentially that the trade is really slow. You can see the year on year. This was from the RAP report. This is the 0.3 carats to 0.3 carats to 3 carats, and how on year it's decreased from 24, 23, and 15%. So there's been a severe decrease, which is again something that was discussed last year, but something that I really wanted to highlight, again, making it so tough for us as juniors to compete in that small stone space. And in general, all of the majors also really struggled. De Beers, Petra, and Rio Tinto all also reporting on declines in the volumes of diamonds coming from their mines, and that it's really just been quite a tough year for everyone to be involved in. And how do we create this additional need and additional revived energy and interest in the market? So then I also went into looking at the exploration trends specifically for diamonds, and And this was published by S&P 500. It was for the 2022 results because they haven't yet released, obviously, 2023. And you can see from an exploration perspective from 2008, how we've really, this chair's in the way, how it's really gone down and how we're really, really struggling. And again, from an exploration side, for us to bring on projects, we really do need a bit more funding in order for us to find these mega deposits that everybody's interested in us finding. I've gone and looked at what the total spend was, or what has been published, which is $232 million. And what was really encouraging for me is you can see Africa is at $60 million, which is really exciting. And what's further actually more encouraging, because I work in a number of different commodities. What's really, really great about the diamond industry is that they're putting a lot of money into grassroots, which is not the case at all when I looked at the copper and gold markets. They were looking at roughly about 10%, whereas, I mean, you could argue there's about a third of their budget is going into grassroots. So that's really encouraging from an exploration perspective, that people are still interested in developing the diamond markets. But what is dominating the space is the majors. The majors are the ones that are putting a severe amount of money in, which is different to the other commodities. The other commodities that I work in, I would say that the majors and versus the intermediates and juniors, they're roughly 50%. So that's really interesting that the majors are really dominating the space in the diamond industry specifically. Overall, the discoveries of mega deposits is on a downward trend, but hopefully with renewed energy or renewed technology and information, and everybody speaks about big data, we are able to go and use this to start driving our projects and our exploration side in a much more structured and possibly successful way, so that we could look at doing things with our money that would contribute and actually add to a project coming online. So that's the one point. Oh, and the other point that I wanted to make was that essentially not so much in the diamonds, as you can see, because like I say, there's a third, but a large amount of focus was actually being placed on existing mines and improving on their data, and their exploration spend was actually on just creating a bigger, or their life of mine, encouraging that rather than grassroots exploration. And then again, that juniors are, with their already scarce funding and difficult environment, they would rather spend more money on proven assets and results. That's sort of where the biggest spend is there. So really, sort of to close off, I do think that the diamond industry is resilient. What I think is a bit concerning and possibly something that should be discussed more is whether we are dynamic and agile enough to keep up with the changes in the market. Because there's a lot of money that's being placed into it, but it does take a lot of time. So are we agile and dynamic enough to keep up with this change and the consumers? So we are all really passionate about being the real is rare, and maybe that's sort of should be a renewed marketing strategy, is that real is rare, because we've seen now the severity that the lab diamonds is having on the market, and or at least with the smalls and the junior space that I was in and that I'm very passionate about. Maybe there's something that we could be looking at and trying to brand better on why we feel so passionately about it, but get it back to the consumer, because us in the room feel passionately about it, but how do we go and get that back to the consumer to feel just as passionate about it? What is really encouraging again is, like I say, we have so many people that are in the room that are passionate about it, that are here, that are brainstorming, that are aware of it and definitely strategizing back in their places of work. But it's definitely a threat, and it's something that we should be aware of and discussing. What is further encouraging is that Africa is a really large continent, and largely there's a lot of unexplored places that we can go and still investigate. But and fortunately, again, we have a lot of renewed interest with the students being here. They're interested in that market, and hopefully we'll be seeing a lot of other additional projects being brought online, cheaper, using better exploration techniques and extractions, and really just using modern data in a good way, and AI, well, not 100% on AI, but using some form of additional modern technologies to direct our exploration efforts moving forward. And that's really my talk.
Thanks for a very interesting look at exploration. Do we have any questions? James?
Thanks, Sarah. An excellent presentation. A couple of questions.
Yes.
How much did your project cost at the Save River, and how was it financed?
So we were a junior on the Australian Stock Exchange. I really can't remember how much it cost because that was over 11 years ago, so I'd really have to go and look. But they definitely looked at a more lucrative option back, or looking up north in the Ruby project, and they were able to sell that as a more exciting project than rather the Save River.
Other questions?
John wants to ask.
Sarah, thank you for the presentation. I noticed your diamonds you did find, they were all gem quality. I know upstream in Zimbabwe at Morange, you're looking at maybe 10% gem, the rest bought, and I was just interested in looking at your production being all gem quality. Is that a true reflection?
So that was the diamonds that we found. So that was, I think, possibly part of the whole thought and concept that they wanted to go and revisit, and possibly why they didn't continue with the project, was that they were hoping to get, like you say, these more bought-based diamonds and a much larger value, and then, like you said, much better gem quality. So the theory was, well, possibly it came from Meroe rather, but instead of furthering on with the studies and looking at more size frequency distributions and looking at producing more, it just wasn't feasible for the money that they wanted to spend on the project any further.
Sure. Thank you.
Thanks, Sarah. It's great to see the views of a young person, and I think we should be listening carefully to more of them. Just on Merewa, and John might want to comment, he's worked there extensively, or not Merewa, Zimbabwe. You know, the Morange diamonds are 1,000 million years old, billion years, and really poor quality, whereas Merewa is far better quality. And there are undoubtedly a lot more of those 600 million year old kimberlites. You know, Merewa, I think, is about that age. There's Phoenicia down the road, and there'll be a lot more, John. And the last comment for me here is again what we've heard today. You know, that project was in Mozambique. We've heard about projects in Angola. You know, we haven't heard about a real project in South Africa. And that has to be, and we've heard about Lesotho and the great work that people like John and Debbie are doing there. And credit to Lyndon, and he was very polite at the start of his presentation. You know, we just don't see the same initiative here in this amazing country. So, you know, what's going on? And where are all our young students, you know, going to be employed? So, you know, somewhere we need to, and particularly the young people, need to be stirring the pots about the future of our exploration and mining industry. Thanks, Tanya.
Okay, just concerned about the cost of the exploration, and I just want to find out, before doing this program, didn't you, as an exploration, consider looking at the pre-studies? Because before putting money in this kind of project, you have to do some pre-studies to know that if the target is prospective. And I remember in the exploration, you can also look at some, I know in those areas like Mozambique and other countries, you see artisanal workers.
Yes.
And then they can also give you some indication. I don't know if you look at that. And I understand it's junior, but why not consider also looking at primary deposits?
So Mozambique really is off the Kraton, and it's not sort of an area that we would be able to target as a primary source. And there were no artisanals, so that was a bit of a sort of concern in general. But we were hoping that with the gravels being much lower than the ground and not being exposed at the rivers, that we were hoping that the paleo channels, essentially that's what we were after, had been preserved, and that's what we were looking for. But it is obviously definitely a concern. But I think that's part of exploration, is that it's pretty risky, but if you're able to make it, then you are. So that I think is possibly why, you know, we only have a less than a 1% success rate, is due to the fact that there's so many factors that you have to look into. And I suppose that was the point of going there, was to go and test this hypothesis and see, was it feasible, and, you know, would we be able to make it to markets, and was it monetarily feasible?
Any other questions for Sarah directly? I've got one based on Sarah's presentation for the young folk in the room, and I'll get back to you directly. You said that on a molecular level, real diamonds are pretty much the same as...
Lab grown.
Okay, perhaps we got the wrong word, but... Lab-grown diamonds, in the eyes of many people, are the same as real diamonds. You young people, younger than 35, the rest of us, please go to sleep. Because you're not going to be buying many diamonds. Would you rather spend more on a real diamond or less on a synthetic stone, or not synthetic, lab-grown stone? I think that's a concern, a real concern that our industry needs to follow. Because it's the young people who are going to be buying these things. And I see two people leaping up and down at the back. Ingrid, you first. Yes, they are.
So I think Karen and I are going to say pretty much the same thing. Diamond is carbon, pure carbon. It's one of the few minerals that is, you know, made up of one element alone. But on an atomic level, they are not the same. That is why the detection instruments that my extremely intelligent physics colleagues in Maidenhead design, they can tell that difference between a laboratory-grown diamond and a natural diamond. There are two ways that laboratory-grown diamonds are grown, either in these very big high-temperature, high-pressure presses. You use metallic catalysts, and you know, you melt your flux, and the diamond grows like that. They incorporate atmospheric nitrogen, which doesn't have the time to aggregate into clusters. So it gives a very typical kind of amber-orange color from single nitrogen. You can pick that up with an FTIR instrument or see it visibly. Now they're managing to grow them quite cleanly without a lot of inclusions. And you can you can actually take that nitrogen out, you can make better colors, you can dope them with boron and turn them blue. Then there's another method called CVD, which is chemical vapor deposition, and that is basically a microwave on steroids. and you grow your diamonds from a plasma. But you have a very different growth instead of your normal cubic or octahedral diamonds that grow in the mantle. You form a sort of layer by layer growth. And so when you do things like photoluminescence and cathodoluminescence, you have very different zonation in these diamonds, plus the difference of your nitrogen content and aggregation state or absence in CVD and luminescence. Many techniques of telling you whether it is natural or laboratory grown, but it's based on actually how that atomic carbon is crystallized into the lattice and with the impurities. So for me, there's just no way that they are the same thing at all. And then for me, it's also about the story, the whole association, something that comes from perhaps as far deep as 600 kilometers, some of Debbie's stunning pinks, these sublithospheric diamonds, something that you cooked up in your microwave a few weeks ago just doesn't cut it for me.
Okay, so I have two comments. So one is following on from Ingrid's. Obviously, I'm a geologist, so I prefer a natural diamond. I prefer a diamond that is rare, it's coming from super deep in the earth, it's coming from an inaccessible place. And a comment that I've sometimes made to the trade is, if you have two minerals, for example, a feldspar, one is coming, you tell a layperson, this piece of feldspar is from the moon, and this piece of feldspar is from your backyard. People will immediately be drawn to the one from the moon because it's coming from some foreign, inaccessible place. And so that's a kind of an analogy I use for natural diamonds as well. In terms of the synthetics, or the lab-grown diamonds, of course, it's fairly simple now with the correct techniques to tell the difference between an HPHT, a CVD, a treated, and a natural stone, if you have the correct spectroscopic techniques. But I'd like to now get a bit more philosophical, perhaps, and people often are wondering about the demand for lab-grown versus for natural diamonds. And I think a bigger issue is that the cost of living. Younger people don't have the budgets for houses, for children, to get married, and so they're not concerned about having a huge, big natural diamond. They're like, do I even want a diamond as an engagement ring? Or do I just want a ring? Do I even need a ring? And so I think we're very concerned about keeping up the demand for natural diamonds. But I think a bigger concern among the younger generations is the cost of living. They can't afford houses, they can't afford to get married, and so for them, this diamond debate is esoteric. It's a luxury good, right? Mm-hmm. And do they need it? And would they rather just? They don't know what we know, the spectroscopic differences, between CVD and HPHT and natural. They don't have that same. We've drunk the Kool-Aid. We're in the diamond industry. We love natural diamonds, but for someone who's considering, buying a house, buying a car, do they need a natural diamond or they just want a diamond? They can't tell the difference. It looks the same to them. And so that's something that we need to grapple with in the industry is an effective marketing campaign if we want to keep the demand for natural diamonds up. And certainly as a scientist, and Ingrid and I have spoken about this a lot, certainly if we don't have natural diamond mining, we don't have access then to these rare specimens from the deep earth. Because apart from the jewelry industry, diamonds are a very important sample that we need of the deep earth to understand deep earth processes. Diamonds and the inclusions and their host rocks have taught us a lot about our planet. And so if we don't have demand for natural diamonds, we don't have diamond mining, our scientific samples go away. So certainly, I would love for natural diamond mining to continue. I'd love for there to be demand for natural diamonds because we need samples to analyze for science. However, we also need to be realistic about the cost of living today and about young people and whether they actually are even interested in buying diamond engagement rings. Sorry.
Good morning, colleagues. Sarah,
Yes.
I'm George from Delgato. I would like to find out mainly about the type or the quality of the diamonds that came out of the Save River project, taking into account that the primary deposits were in Zim.
Yes.
And everybody knows the quality of the Zim goods. It's either it's near gem or it's more closer to board or even industrial.
So they never spent the money to have them evaluated because they were really small. I think our largest stone was, 1.3 carats. It was really not a big stone. And so it was gem quality, just sort of from the experts, from Tanya and John and Spags' sort of viewed. They were never evaluated, but they were gem quality. But just purely on the size, it wasn't feasible at all.
I'm not a geologist, I'm a layman. I have to say you gave a superb presentation. It made perfect sense to me in geology, the description of how it happened. But you also raised the key issue, which is the lab-grown industry going to wipe out the junior end of the diamond industry? And, I don't know, but the De Beers industry response is, natural diamond, it's real, it's different. You have to buy it because, the lab thing is inferior. But when you're looking at a diamond on somebody's finger at a range of 10 meters, how can you tell the difference? And frankly, who cares? Price is going to determine what you buy.
So,
for what it's worth, thank you.
Thank you everyone for your comments, and sorry to cut you off. Thank you. And I knew that this was going to be really controversial, but I also felt that just because it's controversial, we shouldn't shy away from it. It is something that is very real, and it's something that, like I say, behind the scenes and in everyone's boardrooms, they're talking about it and they are aware of it. But I think that's also possibly where we're going wrong, is that why are we not discussing it as an industry? Why are we not aware of it? Why are we not sort of facing this head on? Because it's very much an issue, and it is 100% about the consumer. So again, I know that it's a super controversial conversation in that we are all, well, the majority of us are all very passionate about diamonds here, but we are not the consumer. We need to take that passion to the consumer, and possibly, people got distracted by the molecular level. The point is that we've actually got a threat, and how are we dealing with this as an industry as a whole to deal with this threat that's really, for me, I think the larger stone industry will be fine, but me as a junior, that's where my passion is. I love being in the juniors. I love going through that whole process, and it's really damaging us very, very badly. So that's why another sort of positive is that with being in the ruby industry, moving from the diamonds into the rubies, there was a lot of research that was done, and before sort of this uptake in diamonds, for every one diamond that was sold, there was 2 rubies that were sold, I think in the 1940s. And then with the popular and sort of this aggressive marketing campaign, the diamond industry really took over. So maybe that's also something we should look at, is sort of changing our marketing strategy and looking at how, and I heard it yesterday for the first time, possibly because I'm an exploration geologist rather than sort of a diamond geologist, but maybe real is rare is something that, or a topic like that is something that could really be pushed and looked at marketing for that passion that we love. But it is something that I don't think that we can sort of keep our heads in the sand. As controversial as it is, it's something that we have to address and be aware of.
Well done, Sarah. Thank you so much for that. George, if you'd come up and...
Good morning, ladies and gentlemen. My name is George Mashinini. I'm from a company called Delgado Diamond Finance Fund. I'm here with my senior, Mr. Mayur Mehta, who has traveled over close to 21 hours from our head office in the US to come and meet this rare breed of entrepreneurs, alluvial diggers in South Africa. He has had an opportunity of himself being a diamantier, a cutter, and a polisher, and he has an opportunity perhaps of cutting some of the most important stones from this province, Northern Cape. So I would like to just make a very short, brief presentation about who we are and what we do and possible collaborations that we could do with this rare breed of entrepreneurs. Delgado Diamond Finance Fund is the first non-bank institutional lender to the diamond industry globally. The current structure of the hedge fund is a SEC registered hedge fund in the US, which was founded by two leading entrepreneurial leaders in the name of Chris Delgado, who is a diamantier himself, and also Andres Ricardo Lucas, who is a finance professional. In terms of how we came into being, many of the diamond people here perhaps would understand the kind of challenges in terms of liquidity in the diamond trade, which mainly started from 2008 after the financial meltdown, where many of the global banks that were supporting the diamond industry started to leave the diamond industry, and from 2013 onwards, the entire global diamond industry lost about $10 billion. And as a fund, we have actually stepped in with the aim of trying to actually fill this void. And just going to the next slide, which actually talks about, I don't know, no, I've done that. Which actually speaks about the type of investors that we have at our stable. We've been very, very fortunate and privileged to have people that are actually high net worth individuals that are believing in this industry. We have among our anchor investors, we have institutional sovereign wealth funds and US pension funds that have injected about $500 million into the hedge funds for us to really try to assist the global diamond industry. And the quality of our partners not only attest to the soundness of our strategy and our lending capacity, but also to our long-term commitment to provide sustainable financing to the diamond industry. Our borrowers, since our inception in 2018 so far, we have been privileged to finance, among others, the most prestigious companies in the diamond supply value chain, ranging from publicly traded mining companies to large multinational manufacturers, or as some call them, site holders, as well as polished diamond traders and luxury retailers alike. This has really made us a unique alternative financier to the diamond industry. Just a small brief overview of our management team, which is mainly comprised of diamantiers or diamond professionals and bankers. And also we are headquartered in New York and have regional offices in Palm Beach, Dubai, Johannesburg, and London. Soon, I think in about 60 days, we will also open Gaborone. Due to our understanding and expertise in diamonds, jewelry, and watches, we are comfortable with them as an asset class. That is one of the key differences that sets DDFF, as we are often called, apart from the commercial banks. Types of financing, DDFF is able to craft a finance program to meet your company's specific needs. Some of the examples are below, mainly in this instance, or perhaps for this audience per se, one can make an example of run-of-mine financing, where miners can receive financing immediately on their monthly run-of-mine production, while DDFF arranges and places goods at the tender house of the miner's choice in Dubai or Antwerp, notwithstanding that we can also finance the run-of-mine production in Kimberley and Johannesburg. This dramatically reduces the miners' cash flow, which is a very, very challenging liquidity problem at this current moment for many of the alluvial diamond miners. I believe perhaps for those miners that have had a fortune of making a good money when the market was hot in 2021 and 2022, liquidity in the next couple of months would be a major issue, as many of the alluvial miners are looking at perhaps withdrawing their run-of-mine production, just to simply try to understand where the market is currently going. Number two, among the examples that we have in terms of crafting a custom-made financing program, we can also do a downstream partnership financing, where for those alluvial miners that are fortunate to be able to recover specials, your 10.8 carats, the fancy color goods, we can definitely offer them a partnership deal where Delgato would be able to actually purchase the rough and cut it and share the profits with the miner, thereby allowing the miner to actually build a downstream revenue model and to be more exposed beyond the mine gate. That also allows us to also assist miners to really benefit from an ecosystem that we have built. Among others, we have built a state-of-the-art manufacturing facility in Dubai, which is the largest factory outside of India in the Middle East. And also we have another facility in in New York, where we are actually specializing in large goods and fancy colors. And we can also go even further in terms of marketing, where we could assist miners to really get maximum valuation on the goods that we would have financed on the polish side through leading auction houses such as Christie's and Sotheby's, and also even make possible introduction to miners that are looking at really beneficiating their special goods, where we could introduce them either to high-end jewelers in the US or even masons, as they are called, in the US, to really try to assist miners to maximize the value of their special goods. I won't necessarily touch on the manufacturing finance because we don't have any manufacturers around here or any other financing that we are doing. But in the main, we see ourselves not necessarily as a substitute to your traditional banking in terms of access to finance in the trade, but we see ourselves mainly as a strategic partner to the global diamond industry. So among the things that we can bring through the relationships is that we can market the goods, and we have close relationships with luxury retailers and auction houses, among tender houses. Many of the leading tender houses, both in South Africa and also in Dubai and Antwerp, we work with them hand in hand. We can also bring a very unique element to our relationship. As I've mentioned earlier, we have a cutting and polishing facility, and most importantly, we can also become a de facto advisory board to many of our clients who are either looking at branding their diamonds or actually trying to maximize the value of this rare gem that they are mining. And added value, our ecosystem is valuable. We have a unique view into many of the industry's best companies, knowing what they have or what they want. We work to create benefits to our clients, and we often help our clients source rough or polish or place an important item where it might be needed for sale or more. Our facilities range from a minimum of $50,000 up to a max of $25 million per client. Our LTV value, it's anything between 70 to 80% of the liquid value of diamonds, jewelry, colored stones. Colored stones, it's another thing that we are doing. In the ruby mining in Mozambique, we are heavily involved in that space. Our facilities range from 1 month to 6 months with an option to renew. You can pay back principal anytime without prepayment penalty. There are no setup fees, shipping, insurance, or storage costs. Thank you. That's my very short presentation for financing. Thank you so much.
If they have,
Okay.
If they have any questions.
If there are any questions, we'd be very happy to answer that.
Delgato also has a stand next door, so please feel free to pop on there and chat to them. We have time for one question.
Thank you. The question revolves around the real issue that specifically the diamond and alluvial industry is facing. We do not have a bankable ore body, and normally our biggest issue is to get to the diamond, and not while we have the diamond in hand. There are many facilities that can assist and address the liquidity, but it is financing to get to the diamond, specifically in the smaller alluvial side. Is there any way that your company can maybe devise a plan around that?
So first, blessed morning. We are creating the 5th C. Of course, what your question is, we are facing every day to enter in the South Africa zone. But at present, we don't have solution because of the risk involved. And this is not a banking system. We are a private fund. And we are trying to create a bridge between the liquid and your sale of diamond. Plus, as George, my colleague, said, we are adding the value of your diamonds because we know the pulse of the market. So if you will sell today your diamonds, you will get 30% less. When we come back inside, you can take the finance from us today and cover that risk of 30% and sell after 3 months or 4 months when market recover. I understand what you are saying. We are thinking on that matter, but because of risk involved, at present we are not able to do that. Thank you.
Okay, everyone, I think we're thinning out a little bit, but I'm hoping that our second panel discussion is going to be as interesting as yesterday's was. So this morning, Gert van Eklik is going to chair the session, and it is on the ASM policy document. So he has some colleagues with him, and he will introduce them, and over to Gert for the discussion.
Thank you so much. I just want to shortly introduce my panelists. On my left here is Willem Butler. He's, I call him a strategist. And then in the middle there is Leilani from Swartboy, from Alexkor, the state-owned mine. And on her left is my favorite geologist. So welcome to my panel, and ladies and gentlemen, I want to start the session by making a general comment. And this new policy was published in the Government Gazette. I think it's about in May the previous year already, and to SATPO as an organization and myself in person, I was really excited about the fact that for the first time in the policy document, government acknowledged shortcomings of the current legislation. They specifically mention Section 27 of the MPRDA, and it is also therefore one of SATPO's initiatives that we, through the Minerals Council, are really getting into this policy document. From a legal perspective, to present to government before policy changes to legislation. That is my opening comment, and I am now going to ask my panel a couple of questions around this policy and how they interpret this. So I'm going to start with you, Willem, next door to me. The company EOH is a prominent technology and people solution player in the industry. And I know they supported you to be present here today. Could you please provide the audience with a brief overview of EOH with a relation to the draft policy of artisanal and small-scale mining in South Africa, as well as your project's goals and scope in analyzing the said policy?
Thank you, Gert, for that big question. I'm going to pretend that I'm used to sitting here as part of the panel, and hopefully my nerves will settle soon. Yes, EOH, big technology provider with 2 business units, the IT side or digitalization side, actively involved in the mining industry, and then also a people solution side where they provide resources to the mining industry as well as other industries. To the second part of the question in terms of the link between current EOH and the policy, the link is at the end, the outcome that I think we all want to achieve, and that is community upliftment and the informal transitioning to the formal.
Thank you, Willem. I'm going to tap a little more out of you in terms of community upliftment. What are you looking at?
Saved by the bell. So, Gert, as you know, the policy and the limitations of the policy talks to how big and small work together, and fixing that aspect of the policy will definitely have a positive effect and a ripple effect on communities, how the unemployment issue within communities is being addressed, specifically within the Northern Cape. So that's my short answer to your question. Yeah, I don't want, if you want me to elaborate further, please let me tell me.
We'll get to that later. Leilani, from your perspective as being from the only state-owned diamond mining company in South Africa, and really situated in the heart of artisanal and small-scale mining possibilities. How do you, as a company, see this new policy playing out into legislation, and what would you like to contribute to really have this policy as an effective tool to uplift and create the necessary jobs specifically around artisanal and small-scale mining?
I'm also nervous. Thank you. Alex Gore have initiated a project with regards to artisanal mining. We have looked at areas within our mine in Alexander Bay to help the artisanal miners. We identified 3 women, and they started small little companies initiated by DMRE. So we've worked with DMRE before on projects to uplift the artisanal miners, especially the women. However, DMRE failed to assist them, and it's been almost 3 years now, and nothing came from it. To be frank and honest, I don't like this policy. It wasn't well thought through. It doesn't take all commodities into account. It focuses on it feels, the policy feels like it is government. The government started the policy, but government will shove it onto other companies, bigger companies, who will be the liability is an issue for me. And the fact that all government departments are not talking to each other, and there wasn't proper stakeholder engagement with this policy. For instance, we're talking about funding. Who's going to fund these artisanal miners? Who will take the ultimate responsibility? Who will do the rehabilitation? I don't like the policy, honestly, and I think more work needs to be done and look at different commodities, and they make reference to gold mining in this policy, but there's diamond mining, there's heavy sands, minerals, and yeah, thank you. I hope that answers.
Thank you, Leilani. I must be honest that it's got various challenges encapsulated in the policy document, and amongst others, one of the items states that there should be coexistence between large-scale miners and small-scale miners. Now, whether it implies that you will have a license within a license is not yet clear to us, but it is certainly something that we're trying to establish whether it is the intention, and if so, what about all the current mine health and safety aspects, and how are they going to make it easier for new entrants to become formalized? The unfortunate part about this policy document is, in my humble opinion, is that it was tabled as an quick solution to the current illegal mining in South Africa. And it is not that simple, and therefore it is vital for us to have these conversations so that we can come up with practically implementable suggestions to government before this turns into legislation. Which brings me, Lyndon, to you. With all your years of experience and knowing the small-scale miner and the artisanal miner, given the dynamic nature of the ASM sector, and I want to reiterate that the ASM is not artisanal mining, it's artisanal and small-scale mining. How do you envision the adaptability of the proposed framework to accommodate changes in technology, market conditions, and evolving regulatory landscapes.
Yeah, thank you. Firstly, I'd like to confirm what Leilani said. I mean, I think this policy raises more questions than it gives answers. I mean, you and I and several other people have, when the draft policy was published in, I think, at the end of 2020, we spent a lot of hours and a lot of effort in recommending to government what should be included in this policy document. And a lot of that would have answered all the questions that you've asked me now. And that was largely ignored. And I mean, that makes you question the commitment of government on how serious they really are to get artisanal and small-scale mining really going. In terms of technology, the problem is the capital limits that's been placed within this policy. There's a 10 million rand limit on where up to where this policy will cover. If you look at the latest technology in terms of the X-rays and things like that, which is probably ideally suited for a small-scale guy, it falls outside of this capital limits. On the regulatory side, I mean, who's going to regulate this? I mean, the DMRE as it is now hasn't even been able to implement the MPRDA after 20 years properly. And a lot of the issues that we're sitting with now is because it's not being implemented properly. Now we're going to ask this often corrupt and incompetent body to come and implement another set of legislation. It's not possible. I mean, I'm sorry. I don't think I've asked all your questions, but it's actually a waste of time to answer them because it's just not a really serious policy document, if you ask me.
Thank you, Lyndon. Yeah, I must also admit that there is currently a process also looking at amending the MPRDA. So, but this is why it's so important for us as industry to give our inputs and enable them to put something on the table that is practically implementable and also financially viable. So at this stage, the process is open and priorities differ from the various departments, and as a matter of interest to our audience, I just want to confirm that the Department of Mineral Affairs were invited on many occasions to be present, and unfortunately none of them here. I do want to applaud, sorry I'm a bit off the topic, but Department of Water and the State Diamond Trader was present. But we need to have government at these sessions. And us talking about it, it's a good thing, but eventually, like Peter Moetes stated yesterday, we need to talk to them as one. And at the end of the day, that would be the solution. But there are, in my opinion, positive trends in the policy documents where they want to distinguish or establish two new types of permits, which is something, in my personal opinion, that can help us reignite especially the alluvial side of it, of the diamond industry. But at the same time, I know from the SATPO perspective, we are really pushing for this legislation to be commodity specific, because each of the commodities have different challenges. So on that, Willem, can you elaborate a little bit in terms of the commodity specificness? Do you understand the uniqueness of the diamond industry, specifically the alluvial industry?
Sjoe, Gert, you put me on the spot because I'm no diamond expert. But like you guys all rightly said, that in terms of the policy, they need to differentiate between the various commodities. If you think about the water, health and safety, they've got various requirements and they're not always applicable across the various commodities.
Yeah, the policy talks about surface mining specifically. So it's not addressing the challenges that the country has in terms of the illegal gold miners. But be that as it may, in terms of surface mining, and I want Leilani to elaborate on it. It appears to be a very lucrative business in the West Coast, where they are really doing it illegally. What's your take on that?
True, on the West Coast they're doing it very illegally. In fact, this week they tried at our mine. They do bedrock sweeping, but they also do tunnels, and that is a major issue for us because if they die on our mining right, then the liability falls on us. We can never stay away from that, and that is an issue that is not addressed in this policy. That who takes the liability, why, and you've mentioned earlier on rights within rights. So Alex Gore has some of the rights there, but the community, the CPA, the Regtersvlei community, also has rights there. And the power to demarcate areas in this is given to the minister. The minister will be empowered. What about the landowners and the existing mining rights holders? Shouldn't the onus be on us? And another thing is DMR didn't take in account the MPRA does not allow for partial closure. So how are we going to deal with it? It is a lucrative business for them, and they're going back in open pits that we as Alex Gore may want to go back to once. But now we must give them that piece of land to be more lucrative than us. And how does the diamonds flow? And good, you've mentioned that State Diamond Trader is here. The small-scale miners want immediate cash, or the artisanal miners want immediate cash. We must go through tender processes, through the dig, which can take up to 2-3 weeks, and they don't want to wait for their money because it's a lucrative business. They want to sell it immediately and get immediate cash. And on the time frames that you've mentioned earlier, 1 to 3 years, it takes, if you invest 10 million, which is not enough, it will take you about 3 years to pay back to your investor. So time frame's not good for return.
Thank you, Leilani. On that note, Lyndon, maybe your perspective in terms of what should we as industry do to have this policymakers and get them to listen to all our issues, and second to that, what's your view on if we could establish a workable and a practical, implementable ASM legislation, what would that do to the smaller side of the diamond industry in terms of growth and job opportunities?
Yeah, I think we first have to take a step back. We've been mining minerals and resources in South Africa for about 140 years. Some of the largest mining companies in the world started up in South Africa. I mean, we're mining gold up to 4 kilometers deep at the moment. How many artisanal deposits do you think are really left in South Africa that can be mined with rudimentary equipment? This is not Angola, it's not the DRC. What is left? Why do we have a policy that's going to be effective on maybe 5 or 6, deposits that can still be mined like that? The focus is completely wrong. The focus should be on generating a junior mining sector, because that is where the resources that's left in South Africa should be mined. There's no place. I mean, in our deposits on the Middle Orange River, if you come there with a pick and a shovel and a wheelbarrow, it will take you a year just to get through the calcrete. Then you're not even on the gravel. On the west coast, and the Zama issue that was probably the reason why this policy was developed, is a policing issue. The guys in the gold mines, those mines should be closed, and the police should make sure that nobody goes in there. Even on the west coast, where they're tunneling now, it's not deposits that's suited for artisanal mining. It's a policing issue. Those guys shouldn't tunnel there. You should go back with big machines and go mine these deposits. So I think government has got this completely wrong, and they are completely out of feel what's really happening on the ground. You're not going to uplift communities with artisanal mining in South Africa at the moment. You're going to uplift it by creating jobs with junior companies mining these deposits. So I don't think it's going to come off the ground. So if you ask me what's going to happen with the small-scale guys mining diamonds, it's not going to happen, because there's not real deposits left that can be mined like that.
On that, Lyndon, what about the bedrock sweepings at the lower Orange River and even along the coast?
Yeah, that is the small things that can be done. But it's small. It's not going to make a big financial difference to the communities there. And those are things that should be handled with different regulation. You should have a regulation that allows a company to cut off a little piece of its right or whatever, and go along with it. It'll forego its health and safety responsibilities and give it to these guys to go and mine. That's fine. But I mean, to have a policy to regulate it and to spend all this time that we have spent on it, this time should have been spent on creating the junior mining sector in South Africa. And that's where government has got it completely wrong.
Thank you, Lyndon. On that note, I'm prompting you to urge the audience to come up with some more questions.
Thanks. Yeah, Gert, I mean, I listen to all this, and I've been in this industry 40 years, and I go to Namaqualand, and I see the absolute disaster. And Lyndon's absolutely right on one hand. You know, unfortunately, you and I have been there, and I've been there again recently. And it is just tragic to see what's going on, and it's not just diamonds. And we have all these talk shows, which Lyndon, I think, is alluding to, and yet we've made no progress. And they're, you know, they're practical solutions. For goodness sake, as a starting point, just get someone to go and set up a buying office in Namaqualand. Buy the goods legitimately. Use, I don't know if Luke's here today, use Luke Marriott's software program, technology, to put a value on diamonds. You've got to sell them through the a formal like structure. Pay the guys value less 10 or 15, and make sure those diamonds end up back in the Kimberley process. Because you'll know that there are huge volumes, be it gold, be it platinum, not PGMs, chrome, be it coal, be it diamonds, which are draining this viscous. And yet, you know, we don't have a government person here today in this discussion, and we are seeing this country is broke. We pay back our debt at the rate of somewhere between 1 and 2 billion rand a day. And it's time we all got a wake-up call. You know, this, ironically, this country was built on Kimberley and mining. Now, how do we reassert ourselves positively with community involvement, with sharing the spoils to rebuild this country? And you know, the sadness for me is you see what's going on in Africa. Particularly sad for me was the beginning of this year at the Indaba, which was very well attended. And you spoke to people in Cape Town, and you say to them, wow, you know, why are you here? Well, we're here for the golf and the weather and the wine farms and the scenery. And I'm being genuine. I can introduce you to those people and have a good time. And then you say to them, where are you investing? South Africa? And they look at you blankly. And they talk about, you know, Namibia, Botswana, no-brainer. Angola, ironically, Mr. Jacinto Rocha is now turning the tables on us there. Zambia, you know, these places have been mentioned today. And the rest. So, for goodness sake, the starting point should be, and you said it, where's government? You know, they haven't been to Namaqualand. They haven't seen what's happening on the ground. And obviously, a lot of those people are doing artisanal mining and dying in old trenches and holes to feed their families. A lot of them are obviously doing it within syndicate and illegal structures. And you've done it. You can get the SAPs there next week, and you'll get them cleaned out. And Assi and all the other people that work there, and Corneliuson, next week, they're back. So, you know, unless we come up with solutions that are out-the-box solutions, non-first world solutions, you know, also accept at the end of the day, and people won't like this, we are effectively closer and closer to being a third world country. 20% of us are trying to tell and dictate to the other 80%. So let's please start looking at a South African solution or an African solution to sort the problems that are real and not going away. It's the same as the debate about the climate change and sorry to digress, and energy solutions. Well, we've got simple solutions on the ground. And again, we can't stop coal mining. We're not going to solve the problem with solar and wind farms. And what's a just transition? We are continually trying to play first world solutions in effectively a third world country. And I think in this room, you've got the solutions, but how do we get the rest of the people to listen to them? So that's my concern.
Thank you, John. Yeah, it's a mouthful, and it's actually a pity. I hoped to have De Beers as Peter or even Baron still here today, but their GemFair process that for the first time I saw them publicly speaking about it is seemingly working, and why not invest in the country of their origin to have a similar system. So, but it is also something that we should consider in terms of this policy document to be incorporated where we have a practical working model that we can use as an example.
Yeah, I think, I know you are working with the Minerals Council to try and expand this policy, and I think that's the right way to go. I mean, we need some kind of policy, but it's too restrictive at the moment. The way it is at the moment is not going to make a difference. It's got to be a artisanal, small and junior mining, and maybe junior mining up to a 60 or 70 million capital, but even that is a difficult margin to to put on, because it depends on different commodities, what you can do with 50 million or 70 million rand. But I think you're moving in the right direction, but I think it's just going too slow, firstly. And I think the problem is that the expertise and the knowledge and the will in government to really be part of this process is absent at the moment.
I've seen you were determined to put me on this very hot seat. Thank you, Gert, as well. Thank you, Lyndon, and the panel, and everyone in the room. Policy in South Africa. Wow. A very difficult subject to tackle. If you look at two sectors, agricultural sector and mining sector is not doing well, where agricultural sector is doing exceptionally well. The question is, what are the problems? Where are the problems? The answer is simple. It's policy. The policy in mining is so flooded, such that the system is very, very difficult to roll any policy and make that policy effective, because there's a lot of, my apologies, I'll have to spell spade a spade. There's a lot of corruption, which is very wrong, and it's a hard thing to address. And I understand the reasons why. There's a lot of corruption, there's a lot of self-interest tucked within these policies, and are making these policies very, very impossible to implement. The very policy that you're talking about, Gert, look at what it has done to Sibanye mine. Sibanye gave tailings to the community to fulfill that responsibility, and I'm talking something that happened. John would know about this. It was also addressed in the mining Indaba in Cape Town that you just spoke about, and there's certain family that got rights to mine for those tailings to help the community, but that is just it stands still. It's not working. So we really need a policy shift, and whenever we create or craft these policies, we also need to take into account the interest of the investors, because most of the investors, what makes them shy away from investing in mining and junior and small-scale mines, it's because of these policies that are so flooded by a lot of so-called personal interest. And it's killing mining sector, and it's not doing very well. I understand that you, Lyndon and Gert, you're talking direct to the minister. I applaud your contribution there. I was listening to you, Lyndon, one time. You were speaking at Kaya FM, I think that was 2021 after COVID, which is also something else that also killed the mining sector, and also the regulations have to be changed. Now, these documents that get crafted, sorry, my sister, I've forgotten your name. You just said they don't speak to each other. If you look at all the mining charters, I don't know how many have they created. I know about 3. There could be 4 or more. But all of them do not speak to each other. And the reason why that is so, it is simply because of interest in mining space that there is in certain people, and all of that is killing the industry, the sector. In terms, yesterday, social and labor was addressed, and we have to have partnership between the municipality, the miners, and government, DMRE. That is also another area where there's a lot of incompetence, there's a lot of, you all find these sort of interesting characters my apologies to say so. Thank you so much, John. The question, let me ask then the question to the panel before I leave. The question that maybe could, that I think maybe should be asked whenever you guys sit and craft these policies is this policy going to make impact on the economy, creation of jobs, and what are these policies going to do to enhance the mindset of the investors to actually want to invest more in these small scale mines? Thank you.
Thank you, Simpiwe. I must confess that I've been talking to Simpiwe for almost a year and a half. I'm not sure, since we started talking. And yeah, at the end of the day, this is the reality that we have to deal with. And as much as I would like to help Simpiwe get started, I do need the support of the legislative and regulatory system to enable us. And that at this stage is just not, it's not on. So from my perspective, this type of conversation should carry on, but again, referring to Peter Moete's words yesterday, we should talk in one voice, and we would have to have the policy makers on the other side of the table. Without that, we're not going to progress, and our own experience of when legislation is already on the table and you then have to go through the courts, it is a no-win situation for everybody. So let's be rather proactive and try to get something on the table that is workable. Is there anyone else? I see the time is up. If my Sergeant Major there at the back. Thank you so much. Thank you to my panelists. We really appreciate it.
The next person that we'll be welcoming is Phil Janney from UCT. And Phil has been at UCT for quite a few years, with an interest in the mantle, kimberlites, and particularly today he's going to be talking to us about megacrysts. So Phil, welcome.
Well, I'm a bit abashed because obviously we're transitioning into a whole series of much more academic types of talks, but I have to say that this symposium has really opened my eyes about the issues that the ones on the mining side have to deal with. And so it's great for us academics to see this and understand the scale of the problem. So I don't know if we can lower the lights, but so today I'm going to be talking about the use of kimberlite megacrysts and some of their implications for diamond prospectivity. I'm also a little bit abashed talking about this because there are people in the audience who know a lot more about megacrysts than I do. People who actually have taught me a huge amount, like David Bell and Andy Moore and so forth. So I hope they will forgive my sort of mutterings in this area. I also want to acknowledge my collaborators. Is this, which is the laser? There we go, sorry. So my collaborators, David Bell, UCT, Jeff Howarth, and Alistair Sloan. My former PhD student, Jazeel Carey. Belgian colleagues, Dano Demeef and Thierry Deputé. Mike DeWitt and Richard Price from Lucapa. And my PhD student, Phil Smith Lutzolo, will be talking about a lot more about the Angolan data. So academic research studies of the continental mantle really have primarily concentrated on xenoliths. Xenoliths are wonderful. They are true rocks. They have a mineral assemblage. You can look and see if the minerals are in equilibrium with one another. You can understand metasomatic processes much more clearly when you have a mineral assemblage. But there are times when you don't have xenoliths. When you're dealing, especially in the exploration realm, when you're dealing with indicator minerals and that's all you have, are individual mineral grains. So for us academics in places like Central Africa, where xenoliths are, especially the DRC, where xenoliths are quite few and far between, hard to come by, we have to adopt similar approaches to indicator minerals. And of course, there is also this well-known notion that virtually all kimberlites produce indicator minerals, but only a relatively small proportion produce xenoliths. And so, from my perspective, garnet and clinopyroxene are the most useful indicator minerals. Their major element composition tells us their paragenesis. Their trace element composition tells us about their metasomatic history. And also we can get single mineral thermobrometry by techniques that I'm sure many of you are well aware of. We'll talk about a bit more later. And these kimberlite indicator minerals primarily come from disaggregation of xenocrystic and xenolithic material coming up in the kimberlite pipe. And this is all well known. And obviously the most important and common parageneses are peridotite, whether Harzburgite or Larzolite, eclogite, and then more exotic lithologies like Websterite, or perhaps metasomatic lithologies like the Merid suite. And that's all great and good, but that does not encompass all of the possible origins for kimberlite indicator minerals. There are also these grains called megacrysts, and megacrysts is simply a descriptive term that describes, at least in the kimberlite sense, mantle minerals that are larger than 10 millimeters in size. Here we have some very nice photos of slave craton megacrysts from Busweiler et al. 2018. Here we have a beautiful ilmenite from the quarry kimberlite at Monastery. But, and I think it's not controversial at all to say that there is also a megacrystic paragenesis. That is, indicator minerals can be derived from breakdown and fragmentation of these large megacrysts, and that joins the assemblage of the material coming from peridotite, eclogite, and so forth. But megacrysts are different because they are not just passive passengers like peridotite or eclogite. They are actually, they have a relationship to the kimberlite, and they wouldn't be there if the kimberlite hadn't formed. And I know there's a lot of controversy over, and a lot of debate over the precise origin of megacrysts. I'm going to present my view. This is a cartoon of a cross-section through the lithosphere. This is the lithosphere-asthenosphere boundary, the crust. And to my view, what makes the most sense is that megacrysts are forming in deep networks of veins and perhaps even melt bodies in the lower part of the lithosphere, and that they probably are co-occurring with large vein networks extending out into the surrounding lithospheric mantle. Now this is the precise relationship between megacrysts and kimberlites we can argue about, but almost certainly they have to be related to the host kimberlite, at least in being the product of reaction of precursor melts. The kimberlite is not just a single explosive eruption. There's a history there of a few million years typically in which the melts are interacting with the lithosphere, they're weakening it, they're allowing carbonate-bearing lithologies to get precipitated at shallower and shallower depth until you get to the point where you can actually produce melts with exsolved carbon dioxide bubbles, which then that massive increase in volume allows you to bring to form the kimberlite pipe and bring this material to the surface. But the megacrysts, because they are not just passive passengers like peridotite or eclogite, they have to be interpreted in a somewhat different way, and they may provide very good information about what's going on locally right around the kimberlite, but they are not necessarily giving you an accurate picture of what's going on in the regional lithosphere. And this becomes more apparent when we look at things like Bill Griffin's chemical tomography approach. Bill Griffin from Macquarie University, recently retired, he's built a large part of his career on this approach of taking garnets, doing nickel and garnet thermometry, applying that to a regional geotherm to get depths, and then classifying the garnets on the basis of their trace element compositions to determine whether they are simply depleted or fertile or metasomatized. There are multiple different types of metasomatism. And then there's this sort of the most extreme, which is this melt metasomatism, this red color here. And the interesting thing is I was looking at his 2003 paper, and you see quite a good correlation. The kimberlites and kimberlite clusters that are not associated with megacrysts tend to have quite a small fraction, at least at sort of typical lithospheric depths, of this melt metasomatized garnet type. Whereas if you look at if you look at localities that have abundant megacryst suites, like in this case Premier and North Lesotho and Monastery, you see a huge amount of this melt metasomatized garnet in the lower lithosphere. Now, this is, then becomes a problem of interpretation. I would say that this is probably largely reflecting of what's going on in the immediate vicinity of the kimberlite, but is not necessarily reflective of what's going on in the more distal regional environment. And with that in mind, let's take a look at Central Africa. I've got a project with collaborators that's been going on now for about 4 years, looking at kimberlite indicator minerals from the southern DRC and Angola. This is an area where, particularly in the DRC, the lithospheric mantle is very poorly characterized. Not much data in the literature. Mantle xenoliths are very rare. And so we're really reliant on kimberlite indicator minerals to understand what's going on. But of course, with indicator mineral approaches, you have to make assumptions regarding the paragenesis of the grains and other assumptions that'll enable us to apply, or deciding when to apply single mineral thermobarometry. This is a seismic slice at 150 kilometers depth through the region. In this instance, the red colors are high seismic shear velocities. The green and yellow are lower seismic shear velocities. And I'm mainly going to be talking about the Mbuji-Mayi cluster in the Kasai Craton, which includes both Mbuji-Mayi and Chibwe, as well as a few other localities I won't be talking about. And then to the southeast of that, so this is on the Archean Kasai Craton. To the southeast of that, we have the Proterozoic Benguelu block, and we have the Kundalungu kimberlites, which are located off Craton. And if we look at the garnet compositions, we see that it's pretty much what we would expect. The kimberlites that are placed in a cratonic environment, although they're dominated by G9 moderately calcic garnets, they have significant numbers of G10 garnets as well. Whereas the off-Craton Kundalungu kimberlites have virtually no G10s, and it's virtually all G9 moderately calcic garnets. And if we look at the things like the rare earth element patterns, we also see sort of classic differences between the G9s and G10s. The G9s have these characteristic sinusoidal patterns that are characteristic of initial extreme rare earth depletion by partial melting, followed by metasomatism of very light rare earth enriched metasomatic agent like carbonatite, whereas the G9s show a much more sort of normal pattern with flat, heavy, and medium rare earths and light rare earth depletion. And this was, in 2009, there was a beautiful paper by Bachumike, who was part of Bill Griffin's group, looking at garnets from Kundalungu, Chibwe, Bujimai, and a few other localities, and they had hundreds and hundreds of grains per locality. And they came up with these chemical tomography sections that again show quite large fractions of these melt metasomatized mantle, which they interpreted as being primarily indicating that this whole region was characterized by a large proportion of melt metasomatized lithologies. But is that really the case? Now there's Dan Schulte in his 2003 paper on garnet paragenesis suggested that there's a good cutoff between megachristic and peridotite garnets would be about 0.5 weight percent TiO2. We all know these are sort of guidelines. They're not hard and fast rules. But there's quite a few garnets from Bujimai that are at quite high titanium contents. And interestingly, if you compare the trace element contents of those high titanium garnets with the lower titanium garnets, again, all G9s. So this is just G9 garnets, and the gray patterns are the low titanium garnets, and the red field is for the high titanium garnet. You see the high titanium garnet, much more homogeneous, generally higher rare earth element concentrations, more what you would expect for something crystallizing out of or in equilibrium with a kimberlitic magma. I should mention this is not obviously a rare earth element plot. This also includes other incompatible trace elements normalized to primitive mantle. And if we look at the other kimberlites like Chibwe and Kundalungu, we see also quite a large population with high titanium. In fact, at Kundalungu, you see quite nicely an almost bimodal distribution of these depleted peridotitic G9s and the quite titanium-enriched megachristic G9s with an area of relatively few data in between them. And if we look at temperatures, this is nickel and garnet thermometry using the thermometer of Ryan et al. If you used Canel 99, it would give you very similar distributions. Again, looking at these three localities, Bujimai, Chibwe, Kundalungu, but here characterized by G9 versus G10, G10 being blue, G9 being red and gray, and then the G9s are themselves subdivided between high titanium, which are the red, and low titanium, which is the gray. You see that the high titanium garnets are biased towards higher temperatures. They give you higher averages, higher average temperatures. The low titanium G9s and G10s are virtually identical, give you almost the same average temperatures, and they're not outside, so this is a 1 sigma standard deviation. They're not outside of 1 sigma, but they're still significantly warmer than the high titanium ones, than the low titanium G9s and G10s. At Kundalungu, it's even more pronounced. Again, we only have G9s, but the high titanium G9s are skewed to high temperatures, whereas the low titanium ones are skewed to lower temperatures with quite a significant difference in average temperature. Now, we can also see some interesting things with clinopyroxene. There's many fewer clinopyroxene data. Bachumiki did not look at anything other than garnet. But we have clinopyroxene from all three localities as well. And they mostly fall in this range of the sort of typical garnet peridotite type compositions that extend into the lower chrome area. Let's just ignore these eclogitic ones for the moment. If you look at calcium number versus chrome number, now pyroxenes are great because calcium number, in the presence of orthopyroxene, calcium number is strongly related to the temperature of crystallization, with the higher calcium numbers being lower temperatures. And we see at all three locations, we have this body of data with with low calcium numbers and sort of low to intermediate chrome numbers, which look very analogous to the chrome pore suite of clinopyroxene megacrysts we see in Southern African megacrysts. Interestingly, the Kundalungu trend is displaced to somewhat lower chromium than the Cretonic, Mbujimai, and Chibwe trend. And then we have these down here, which also seem to be sort of following some sort of fractionation trend of decreasing chrome with decreasing crystallization temperature, suggesting pulling chromium out of the magma or out of the melt as it's crystallizing, but also some apparent mixing with a more chrome-rich, sort of more typical peridotitic composition. And these grains up here are very typical to what we see in granular garnet larzolites from the Capville craton, much sort of typical peridotitic CPX. You look at rare earths, all these grains are light rare earth enriched, but the chrome pores show the least light rare earth enrichment. Again, similar to what we see in Southern African chrome pore megacrysts. The more sort of what I'm calling here chrome-rich megacrysts are somewhat more enriched. And then the peridotitic grains have the greatest enrichment, as if they have been experienced metasomatism by a highly light rare earth element enriched metasomatic agent like carbonatite. Sorry, that's right. And then if we look at planetpyroxene thermobrometry from Nimis and Taylor, we see that these chrome pore megacrysts tend to lie at higher geothermal gradients than the, what I've been calling the chrome-rich and peridotitic grains. So they are suggesting that they are thermally different, again, more consistent with equilibration with, or formation from hot, probably kimberlitic melts. And that is, and that they are distinct from these other clinopyroxenes, which all lie on much more sort of typical cratonic geotherms in the case of Mbujimai and Chibwe. And the difference is not quite so severe in Kundalungu, which is off craton, but we do have this body that's at higher geothermal gradient. So, to conclude, a major component of a kimberlite's metal xenocryst assemblage is, in many cases, megacrystic. Obviously, it varies from kimberlite to kimberlite. And these are local products of crystallization and melt rock reaction with kimberlite melts. These are important, and they are telling us something very important, but they are primarily local. There can be areas where you have clusters of kimberlites that are all megacryst rich, but there are also places like Berkeley West and so forth where you have some very megacryst rich kimberlites next to others that are very megacryst poor. And so we just need to be careful to not make too many broad regional generalizations. There are implications for diamond exploration is that these megacrysts don't necessarily have to be regional in extent. But on the other hand, the megacryst producing melts can have a local effect on the diamond grade due to heating and oxidation of the mantle and metasomatism. So they are important, but we just have to be careful about not generalizing too much. Thank you very much.
Sorry. Great talk, Phil, and I think it's great that you're getting the story across that the megacrysts are telling us about the kimberlite event, and I think that's been neglected for too long. Just a comment that's not, it's a question actually not related to your talk, but you see in the literature people saying that the megacrysts come from the lithosphere-asthenosphere boundary. And I've never quite understood where that comes from. Have you looked at that?
Yeah. So I don't think that's really correct. I think the ultimate origin of the melts may be from below the lithosphere or generated, close to the lithosphere-asthenosphere boundary. But I think that there are a lot of issues with thermobrometry, single mineral thermobrometry applied to megacrysts, as you well know. But I don't think that there's strong evidence for a significant pressure range that they form over. And it seems to be, has to be within the lower lithosphere where you have these hot melts encountering this conductive geotherm that's taking the heat out of the melt and allowing the things to crystallize there. I mean, that's probably a simplistic view, but.
Our next speaker is Corinne Smit. Corinne did her master's at UCT and then went on to the University of Alberta to do her PhD on xenoliths from the Atawa-Piscat area. And then she spent some time at the GIA. So those of you also with gemological questions, not only is she interested in xenoliths and diamonds, but also the gemological aspect. And she says she's changed her talk, so she's going to introduce it herself. Thank you, Corinne.
Thanks, Ingrid.
So yesterday, listening to the talks, I thought maybe I'd give a talk that has a bit more of an industry focus, or maybe that some of the industry people would be a bit more interested in. If, however, you did show up to learn about vertebrate diamond ages, I'm more than happy to show you that data afterwards. Just come see me. I'm happy to still talk about that. So what I've decided to speak about instead is the geological processes affecting diamond color. So if you could just make it full screen, please. Yeah, thank you. We saw some really beautiful images of large diamonds, rare diamonds, colored diamonds yesterday. But something that I think the geological community is still coming to grips with, or still trying to understand, is where these colored diamonds are actually forming. What are the processes that influence diamond color? And can we ever get to a point where we can predict where we can find these rare pink diamonds, rare yellow diamonds? We now know blue diamonds are coming from the sublithosphere. But can we ever build these into our predictive models, actually looking for and identifying targets where we can produce these beautiful, rare, valuable colored diamonds? So the reason why we are interested in colored diamonds is the difference in value. So these prices are from Blue Nile, just from the web. They're actually a few years old, so the prices may not be current, but I think the point stands that all other things being equal, I mean, there's many factors that influence diamond value, but if you take a 1 carat round brilliant stone, or you take the same cut stone that has the same clarity and the same polishing features, a colored stone would fetch much higher prices than a colorless stone. And so this is why we are interested in fancy colored natural diamonds, because they are rare, they're super valuable, and if you do have them in your production, then you get very excited about it. So we want to try and understand where these fancy colored natural diamonds are forming in the lithospheric mantle, and if we can get a handle on the processes that lead to their formation. So the structure of the talk is I'm just going to go through a few different colors and then just briefly explain the latest thinking about how we think these colors are forming. So the first example that I'm going to go through are natural 1B diamonds. So these are, in the trade, an old term for them is canary yellow. So they're slightly different to the Cape yellows that John was showing us that they're producing here in Kimberley. They're a lot more vivid, so they're these fancy, vivid yellow colors. And this is due to a particular form of nitrogen in the diamond structure. So when nitrogen is first incorporated into the diamond, it is incorporated as isolated nitrogen. So that is on the left. So that is a type 1B diamond, because it has a single nitrogen or isolated nitrogen substituting for the carbon in the lattice. With time, with temperature, and with increasing nitrogen content, you have this aggregation process. So unfortunately, I see the middle schematic is on that bend in the wall, but type 1AA diamonds have A centers, which are nitrogen pairs, and then eventually with further aggregation, we get 4 nitrogens around a vacancy, and that's a 1AB diamond. So the majority of natural diamonds are somewhere between a 1AA and a 1AB. So the majority of natural diamonds have A centers and B centers. Both of those defects are not color centers. So if you have an A center or a B center, it's actually a colorless diamond. So you start off with isolated nitrogen, which is this yellow, and then as nitrogen aggregation proceeds, you have A centers and B centers, and that's actually the majority of natural diamonds have these A centers and B centers. There is sort of a side defect that forms in this aggregation process. So during the aggregation process from A to B, there's a defect that's 3 nitrogens and a vacancy, and that's the N3 defect. And that is the yellow color that Jean was showing us in these octahedral diamonds from Kimberley. So it's actually the A centers and the B centers have nothing to do with color. It's actually this other defect in 1AB diamonds that then give them this paler yellow color to the vivid yellow that we see in 1B diamonds with isolated nitrogen. So where do these natural 1B diamonds actually form? It was previously thought that 1B diamonds are extremely rare, and this is because in the lithospheric mantle, they're at high temperatures, they spend billions of years at these high temperatures, and so that is why the majority of diamonds are aggregated. However, more and more we're seeing in diamond productions from around the world that there are these canary yellow, fancy vivid yellow diamonds in the production. So they're a lot more common than previously recognized. And so here's just a few localities that I know of, and hopefully some people can share some information and we can expand this map where we can actually identify natural 1B diamonds, these canary yellow diamonds. Here's an example from Canada. This is a deposit that's being developed by North Arrow Minerals. They have these beautiful, fancy, vivid orange yellow 1B diamonds in their production, along with a range of other goods, including colorless diamonds, brown diamonds, and some bort. There's also a type of 1B diamond that has what's called the 480 band color defect. So this is a defect that is associated with isolated nitrogen, and then sometimes you can actually see the color that is actually limited to the specific growth zones in the diamond. So the 1B color or the color associated with a 480 band is not necessarily homogeneous throughout the stone, and so sometimes you could have the color restricted to specific growth zones, which is pretty interesting because it shows that the different growth zones have different defect characteristics which lead to this heterogeneous color in the stone. And so this obviously, if you see a yellow rough diamond, but then you're going to be cutting and polishing it and introducing into the trade, this is something that you would want to identify prior to doing that. So another way that the color is not always homogeneously distributed throughout the stone is that you could have cores or rims of this yellow 1B growth. So you can have this isolated nitrogen only in a particular growth zone. And so in this case, the preservation of isolated nitrogen in the stone must be slightly different because it cannot just be related to time in the lithospheric mantle. In the one case, you have the yellow that is being preserved in the core, which is the older growth zone. And in the other case, you have the yellow 1B defects being preserved in the rim, which is the younger growth zone. So time clearly is not the only factor that means that we have preservation of these colors in the diamonds. So these are just examples from Canada and from Arapa showing the heterogeneous distribution of the yellow within the stone. And so potentially in the one case, nitrogen content is a more important factor, meaning that higher nitrogen content means that the aggregation process is enhanced, whereas in the other case, potentially the shorter timescales are the reason for the preservation of 1B nitrogen and the yellow color in the Lac de Gras goods. So here's an example where we were able to find out the age of a certain suite of these 1B diamonds. So these are canary yellow diamonds from West Africa, from an alluvial locality called Zimi. These had these large, beautiful, I find them beautiful sulfide inclusions inside, and so we were able to break out the mineral inclusions from these stones and determine an age for the diamonds. So we found out that from the rhenium osmium isotopic compositions of the sulfide inclusions, that they're 650 million years old. However, they must have had at least a 500 million year residency time in the lithospheric mantle. So that is taking the age of the diamonds and subtracting the kimberlite eruption age. So these diamonds were residing in the lithosphere for around 500 million years, but you would expect that for 500 million years at temperatures in the lithospheric mantle that you would have some aggregation occurring. And so it's a bit of a mystery why these 1B defects, these rare 1B defects are preserved and the diamonds are still yellow. And so a model that we proposed was that shortly after their formation, they must have been exhumed, tectonically exhumed through collisional processes to shallower depths within the lithospheric mantle, meaning that they're not residing at high enough temperatures. And so that means that the isolated nitrogen could be preserved. And so to summarize, for these fancy canary yellow 1B diamonds, there are three processes that we think are responsible for their preservation. So in some cases, it could be that you have a short mantle residency time, as I discussed for the Zimi diamonds. The other reason could be low temperatures in the mantle, such that they don't have the heat that they need in order to proceed with aggregation. And the other option is that they have very low nitrogen contents, such that the aggregation process can't proceed, which is fortuitous because then we preserve this beautiful yellow color that is really valuable, valuable in the trade. So next I'm going to be talking about some blue diamonds. So this is a rough blue diamond that came through the trade a number of years ago while I was still working at GIA. We now know from a number of studies that blue diamonds have mineral inclusions inside them that are from the sublithosphere. So these are diamonds that are forming much deeper than the majority of other diamonds that we see at the Earth's surface. So this was a study done by my previous colleague, Evan Smith. Here's an example of a 24-karat blue cut stone that he studied. He did Raman non-destructive analyses on the inclusions that he could identify within the stone, and he found that these inclusions are coming from very deep within the Earth. So on the right-hand side, I have just a schematic showing a cross-section through the Earth. So the majority of diamonds that we see at the surface today are forming in the lithospheric mantle. So these are the majority of diamonds that we see. However, we now also know that there are diamonds forming within the transition zone, which is between 410 and 660 kilometers deep. And from the mineral inclusion evidence, we now know that blue diamonds are forming here at the boundary between the transition zone and the lower mantle. What is interesting about these diamonds, though, is that they have carbon isotopic compositions that are not mantle-like. So the carbon isotopic compositions indicate that the boron for these diamonds has been subducted, so that it came from the oceanic lithosphere, from hydrothermally altered oceanic lithosphere. It was subducted down into the transition zone and lower mantle, into the formation area for these diamonds. So the mineral inclusions indicate they're coming from the boundary between the transition zone and the lower mantle. The boron isotopes, the boron itself is actually coming from the Earth's surface. What is interesting about these type 2B diamonds and also type 2A diamonds is that in cathodoluminescence, they show these beautiful dislocation networks. These are formed through deformation deep in the mantle. So it is absolutely characteristic of natural 2As and 2Bs that they have these deformation or dislocation networks in their cathodoluminescence images. So these are diamonds that have been deformed at very high temperatures deep in the Earth. And so one of the challenges that remains is, can we ever target in exploration, targeting for blue diamonds or targeting for sublithospheric diamonds? Because we know that many sublithospheric diamonds are large, they're inclusion poor, so they're highly valuable in the trade. Blue diamonds often are also the larger size categories, and so it remains a huge challenge, is can we ever explore and target for sublithospheric diamonds? So this remains a huge challenge, and I'd love to discuss this with people here, is the indicator mineral suite that we typically use. Those are lithospheric indicator minerals. So we're targeting lithospheric diamonds. And the problem is that sublithospheric minerals, they revert back to lower pressure forms at the Earth's surface. And so a challenge is, can we ever have an indicator mineral suite that shows us that minerals are coming from super deep? Potentially, we need to start getting creative. For example, ringwoodite. Is there any way, if we have low pressure olivine, is there anything in the chemistry that could indicate to us that it used to be ringwoodite? We know from garnet chemistry, if we have excess silicon, it was a majoritic garnet coming from super deep. And so I think we need to start looking at our mineral assemblages and seeing if there is a way that we could target or find out where these sublithospheric mineral assemblages are occurring. And then lastly, I'm just going to go through some pink diamonds. So this is a pink diamond, the image is from Petro Diamonds. It was recovered at Williamson Mine. This particular diamond, we know it's super deep, came from the sublithosphere. It came through GIA, and my colleague Evan Smith was able to Raman some of these inclusions and found that they were coming from super deep. So pink diamonds are pink because of this defect called the 550 band. The 550 band refers to UV visible spectroscopy. So in the visible spectrum, you have this broad 550 nanometer band absorption feature. So the majority of natural pink diamonds have their pink color due to absorption by this 550 nanometer band feature. The defect has not been definitively identified yet. However, it is associated with deformation and with vacancy clusters. So very often what you see is that the pink or the brown color is concentrated along the 111 crystallographic planes of the diamond. So we know it's associated with plastic deformation. However, there are groups working towards identifying what this defect is. However, that work hasn't been made public yet. So the defect is not identified. However, geologically, we know that it is often associated with deformation in the lithospheric mantle. You also get pink diamonds that could be aggregates. This is an example from, I think it's from Argyle. We had an aggregate, the one side is colorless, the other side is pink. So it's the same stone. It must have experienced the same deformation conditions in the lithospheric mantle, and potentially one explanation could be that there's differential nitrogen concentrations in these two different portions of the stone, meaning that nitrogen stiffens the lattice against deformation. And so if you have a higher nitrogen stone, potentially you won't have the formation of these pink color-forming defects. So there's a lot of different varieties and nuances within pinks. Not all pink diamonds are the same. So even though they are both related to deformation in the lithospheric mantle, Argyle and this other locality, Santa Elena, they have distinct characteristics where they have higher aggregation, lower nitrogen content, and the pink color is more diffuse through the crystal. It's also associated with deformation because if you look in the cathodoluminescence imaging, you can see the deformation slip planes. However, most other localities, the pink is a lot more restricted to these deformation planes. So you actually have the majority of the crystal is colorless, and the pink is only restricted to the deformation microtwins in these diamond crystals. So certainly further work still needs to be done in understanding when does deformation cause the crystal to deform in one way versus the other way, and would you be able to predict then when you'd have a more diffuse pink color throughout the stone versus a stone that's largely colorless but has the pink defined to these very specific slip planes. So Debbie Bowen certainly spoke to us yesterday about the new kid on the block, but Argyle up to 2020 was the most famous producer for pink diamonds, and hopefully Carl can now take over where Argyle left off and introduce a lot more pinks into the trade. So Argyle is on the margin of the Kimberley Craton in the Halls Creek orogenic belt. And so there's been diamond dating studies done, there's a lot of inclusion work, a lot of work has been done on the Argyle diamonds, and now the model that is preferred is that certainly the diamonds are very closely associated with subduction, and they occur here in the margin of the Kimberley Craton. But the inclusion studies and the geothermal barometry that's been done shows that these pink eclogitic diamonds residing near the base of the lithosphere. And so potentially the deformation that is inducing the pink color is actually not from subduction, but rather because these diamonds are residing near the base of the lithosphere, where you have a lot of deformation occurring near the boundary of the lithosphere and the asthenosphere. So these diamonds are residing near the boundary of the convecting mantle, where mantle convection could induce drag here along the base of the lithosphere. And potentially that could be a reason why these Argyle diamonds are pink. Certainly deformation is a well-known characteristic of many peridotite xenoliths, eclogite xenoliths in the lithosphere. Here's just an example of a sheared peridotite here from South Africa, but certainly the dynamic environment at the base of the lithosphere may contribute towards diamond deformation and the origin of pink diamonds. Here's just a further example showing that many peridotite xenoliths in the lithosphere are somewhere along the cycle of deformation. So deformation is very common in the lithospheric mantle, and certainly that's something that I would like to try to do is relate deformation in the lithosphere, deformation that we see in peridotite xenoliths, to the diamond populations at particular localities to see if we can link these two processes to each other. There is also the sublithospheric pink diamonds. So Juina is a famous locality for these pink diamonds. I've already mentioned that the diamond that Petra recovered at Williamson. However, not all sublithospheric diamonds are pink. A lot of sublithospheric diamonds are deformed. I've already mentioned the dislocation networks, but this is a diamond from Juina. It's a colorless diamond. We know it's sublithospheric because of the mineral inclusions. And you can see in the cathodoluminescence, you can see a lot of deformation, you can see the glide planes, you can see some of the dislocation networks. However, why is this diamond not pink? So deformation doesn't always equal pink. And so that is something also that we need to try and unravel and understand. So there's also some localities where the exact geological environment for pink diamonds are not fully understood. These are some diamonds that I saw when I visited Lomonosov in Russia. A lot of fancy yellow diamonds, also some pinks and some greens. This is a locality that is in a region that experienced lots of tectonic deformation. But then there's Voorspoed here in South Africa, which is right in the middle of the Kaapval Craton. And why are there pink diamonds at Voorspoed? And so just some hypotheses that I'm throwing out there, because there's a lot of unanswered questions here. So at Lomonosov, potentially, there's a few options. There are pink diamonds there. We know that geologically it's in an orogenic belt, so there's a lot of deformation, collision, mountain building that occurred during the Proterozoic, so that could be a reason why we have this highly deformed population. Potentially, they could be near the base of the lithosphere, in a highly dynamic environment where lots of deformation is occurring. Or potentially they're from the sublithosphere. So we won't be able to decide between these three different scenarios unless we had the mineral inclusions. So we can have depth constraints, and if we had the xenoliths in which these diamonds occur, then potentially we could do a study where we could really unravel which of these scenarios it is. The same thing with Voorspoed. Voorspoed is here in the middle of the Kaapval Craton. Are these Archean diamonds that were deformed during collision of cratonic blocks? We know that the Kaapval certainly isn't stable. We know that there's multiple episodes of plume eruption, large igneous provinces. Could any of these tectonomagmatic events have contributed towards deformation in the mantle? Similarly to the hypotheses that I put forward for Lomonosov, diamonds could also be near the base of the lithosphere or from the sublithosphere. And so here's just a slide I put together for what I think needs to be done in order to understand the geological origin of pink diamonds a little bit better. So aside from establishing the nature of the defect actually causing the color, that needs to be identified. There are a number of things that we can do in order to understand the geological origin of pink diamonds. The one is we need to do inclusion studies on pink diamonds, and I understand that this is a difficult proposition because these diamonds are extremely valuable. However, if we could have offcuts of stones, if inclusions could be saved during the cutting process, that potentially could be a way that we could get a handle on the depth of origin of these diamonds while still making the diamonds available to be sold to the trade. So if we could do inclusion studies, and then we could determine whether these diamonds are coming from the sublithosphere or from the lithosphere. Then we could also do pressure and temperature determinations on the inclusions themselves. It would be great if we could determine the age of pink brown diamonds. Once again, inclusion-bearing diamonds, and it's a destructive study. So I understand that this is a difficult proposition because of the value of these goods. We also need to understand the impact of deformation on diamond crystallography, because deformation does not always result in coloration of the diamond crystal. And so this work doesn't necessarily have to be location-specific, but certainly we need to work towards understanding what the influence of deformation is on the diamond crystal, and if we can predict when pink will form in relation to deformation versus when the diamond will become brown, or whether the diamond will remain colorless. And so I think that kind of sums up what I think the work that we as a community need to be trying to do to understand the origin of pink diamonds a little bit better. And then on a lighter note, the origin of some pink diamonds are fairly well constrained. We know they come from a lab in Oregon.
Thank you very much. Thanks so much, Corin. And I think it's really important the way you've provided a bit of that context, why some of us geologists want to bash diamonds and get the inclusions out and date them, etc. For the people in the trade, you guys actually don't want the inclusions. So can we get in the forum and actually partner that we can get what we need and then feed the information back to you guys? It's really, really difficult. This work often takes looking through production through millions of diamonds to get the data. And for those of you who were wondering when Barend was talking about 4D prospecting, the last dimension is time. We are looking at the way the mantle evolves with time, and that's why time is a hugely important factor in our prospecting, because we're now realizing that not all diamonds are 3.2 billion years like was sort of proposed at, in the 80s by Steve Richardson, by really good work with what equipment was available at the time. As always, nature is so much more complex. And again, that's that distinction with laboratory-grown diamonds. So I'm sure there are lots of questions for Corin. Thank you very much.
Well, what is real? What's your definition of real? Natural, okay. But it doesn't disprove that it's not been treated. You can have a natural diamond that's been treated in the lab, and so that's also a very important distinction to be made. So goes through a gem lab, just because it has a mineral inclusion doesn't mean you don't have to be extremely cautious.
Corin, just a second question. I always found it very interesting that Argyle diamonds from a Proterozoic Kimberley 1200 were, mostly pink, the ones that were decent. On the other side of the Kimberley at Ellendale, there are some pinks, but they're extremely yellow, lots of vivid yellows, just as a point of interest. Yeah.
Yes, so that's certainly something that needs to be unraveled, is why Ellendale on the one side of the craton is producing these very fancy, vivid yellow diamonds. They're not 1Bs, they're actually, I think they're also capes, so it's the N3 defect. So they're highly aggregated yellow goods. And then the other side of the craton, you have these fancy pink diamonds. So clearly, it's not simply that you have an orogenic region where you have subduction-related processes causing deformation in the lithospheric mantle, because if that was the only similarity between these two localities, you would expect the similar colors and similar goods. So yet, on the one side of the craton, you have these beautiful pinks, other side, you have beautiful yellows. And yes, further work needs to be done to understand why that is, and can we ever predict when we'll have these differences.
And Baxter, have you got any comment on that? Is he still here? Right?
But the Ellendale pipes, I think they're much younger in any case than Argyle, correct? Yes. As I remember it. Yes, they're brand new, they're just the other day. And I don't think for a moment that this correlation should be made, because I guess the mantle has changed vastly from the time of Argyle, because the movement of the mantle, or the crust over the mantle, so the choice of mantle material to supply these diamonds would surely be different. I don't know. That doesn't answer your question, because...
No, I think that's a good point, and the diamond ages are actually fairly similar. So the Argyle diamonds are 1580 million years old, and the Ellendale diamonds are 1400. So they're Proterozoic diamonds. However, a large amount of time has passed between diamond formation and then lamproite eruption. And so deformation obviously is post-growth. And so a lot of geological processes could affect the diamond color post formation.
Yeah. Yeah, that is the case. I think there's huge changes in the mantle or the crust in relation to the mantle at the times of these eruptions.
Yeah, certainly.
Fascinating paper, well done.
Thank
and
you.
it brings on many questions, particularly on our yellow diamonds. What I didn't point out in my presentation the other night that, excuse me, 1 in every 40 or 50 come out as an intense yellow, beautiful intense yellow. Question is, where are they being developed in association with each other, the capes, the fancy yellows, the intense yellows, and the vivids? I meant to say vivid there. 1 in every 40, 50 is a vivid. 1 in every 30 is an intense yellow. Are they getting their color coding in the same zone, or is there another story to tell?
I think that would be very difficult to answer unless we can get hold of some inclusions. If we had the vivid yellows with inclusions, and then we had the paler yellow also with inclusions. And then we can say what the difference in depth is between the formation of these two diamond populations. And then what we could also do is carbon isotopes, nitrogen isotopes on the diamond themselves to understand where the fluids and the melts are coming from to form these diamonds. Because potentially it could be that they're forming from very similar fluids. However, they just have slightly different nitrogen contents, meaning that the fancier, more vivid yellows are remaining unaggregated because they have lower nitrogen contents, or because they're at shallower depths in the lithosphere, so they're not experiencing as high temperatures. And that the diamonds that are more aggregated and the paler yellow colors, they could be at higher temperatures, higher depths, greater depths in the lithospheric mantle, or they could have higher nitrogen contents, meaning they're becoming more aggregated. So there's certainly a lot of options that could explain these differences. However, actually pinpointing what the exact reasons are for any particular locality requires the community to do some destructive analyses on these stones.
On that, my second point, the inclusions, they are recoverable. In the manufacturing industry, most of these inclusions are avoided by sawing them out in one way or another. And wouldn't it be great if the industry brought out another certification system, and you certify the inclusion with the GIA certificate, and everybody knows exactly where that stone comes from? I think it's very possible to pull the inclusions of important stones back to a lab for probing.
And that's certainly how many of my colleague Evan Smith at GIA, many of his studies were done on these offcuts because they had relationships with the diamond cutters where we were able to ask them to preserve the inclusion-bearing offcuts during the polishing and cutting process. However, it's not always possible, because there have been cases where people would be very cautious in cutting a stone because of the graining. And so if you have a pink stone with lots of graining, you may not want to laser cut this. You may want to just polish through it very slowly, and in that case it's not possible to retain the inclusion. So certainly there are many, many constraints, but I think it would be great if we could all have a good, productive conversation about this in a way that we could get information that we can better understand these stones while still making the stones available to the trade and selling them at premiums that we all want. Yes.
Thank you, Karen. Can you hear me? Okay. Karen, thank you very much for your talk. It was really very interesting, and I would like to collaborate with you as much as I can, especially on the pinks. We have seen the results of some of the offcuts of our stones, and I don't know whether or not you would be able to use it, because after it's been laser cut, it is no longer looks like a diamond anymore, and you can't see.
You can polish off that laser surface, right? So that's what we do routinely for our research samples. We laser cut a double-sided plate, and then we stand at the scythe and polish off that laser surface to make it a beautiful transparent stone again. So certainly, I don't think that would be a hindrance.
Problem. Okay. So then I will, if I have a chance, I will try and keep you a piece.
Oh, that'd be amazing. Thank you. Yeah, let's chat.
Hi, Karen. Just a quick question on the Argyle violets. What causes that?
I don't think that has been figured out yet. So certainly the Argyle violets are unique. As far as I know, that color only comes from Argyle. I think I saw Yesterday, someone was talking about some violet stones or some purplish stones, but I'm not sure if that's the same color origin as the violets that are coming from Argyle. So as far as my understanding is that the defect causing the violet has not been definitively identified yet. However, there is an association between the violet color and the stones being very hydrogen rich in terms of some CH defects that you could see in infrared spectroscopy. But I don't think that we know the color origin for those stones yet, unfortunately.
With regards to the lattice with the 4 nitrogen atoms and the vacancy in the center, do you see more stress in those stones with those nitrogen atoms?
Yeah, certainly all natural diamonds will have some strain in them. If you look at a diamond under cross polars, you can see the strain ubiquitous throughout the stone and certainly also around the inclusions. And that definitely is a defining feature between synthetics or lab-grown diamonds and natural diamonds is look through cross polars, look for strain. HPHT diamonds will have very little strain compared to natural stones. I don't think necessarily there's a relationship between the more aggregated nitrogen only and strain. I think there's many factors that could cause strain in the stone. Certainly the aggregation process is one of them, but I don't think that's the only factor that you take into account when considering strain in a natural stone.
So there isn't a comparison to take between the 1Bs and those who are more aggregated?
No, because you could have 2A stones with no aggregation that are highly deformed. So I think some nitrogen could cause stiffening in the diamond lattice, and that's certainly a proposal that's been made for those aggregates where you have colorless and pink. The one is, it has the pink color, so it could be nitrogen content causing the difference, and more nitrogen could cause stiffening of the lattice against deformation. But certainly, I think having these defects migrate through a stone is causing some strain, certainly, but I don't think that's the only factor to consider when looking at deformation and strain in the diamond lattice.
And regards to the pinks, are they more plastic deformation that forms? Shouldn't they be more pure to be plastically deformed compared to, let's say, a yellow stone with more nitrogen stiffening it up?
Pure in what way? Pure relatively?
Pure carbon, no impurities.
Well, we know that
the D-color stones.
Yeah, so you can have type 2A diamonds that are pink, but you can also have type 1AB with high nitrogen contents that are also pink. So, no, I guess I disagree with you there.
Thanks, guys. Relative to that question just a little while ago, when we were busy working out what kind of final recovery we do at Cullinan, I was testing virtually every diamond I can get hold of. And we pulled out a diamond at Koffiefontein. It was a beautiful 6-carat pink stone. Early in the morning, and I got the report back that we got the stone. And because I wanted more information to it, I said to the girl who was handling it down there at Koffiefontein, I said, look, go and put that thing through the flow sort machine again. And just make sure you don't lose it, but just, I want to see if we catch that thing once or twice, that it's actually doing that. The day dragged on and I didn't get a reply. And eventually, later in the afternoon, I called up and I said, Zell, what happened to that 6-carat stone? She said, oh, meneer, we put it through the machine and it turned white. And in that lies a stone that had been put through the flow sort about 2 or 3 times. It turned white, and when I spoke to her in the afternoon, she said, but don't worry, it's gone pink again. So
that gives you, it is very small deformation plastically, I'm sure.
Yeah, certainly that is very stressful if you have highly valuable colored goods and they change color on you. I don't think that's desirable for anyone. And so, yeah, I certainly remember at GIA we were very careful with pinks for that reason.
I think Tanya said that we've got to call it quits now. I think we could question Corin for the rest of the day happily on this subject. But we're going to break for lunch, and please thank all the speakers and the panel.
Oh, we're on. Thank you very much. Thanks for the lights. Thanks all for coming back after the lunch session. So today I'm going to be talking about a really interesting suite of rocks, diamondiferous xenoliths. So these are xenoliths from the mantle that the kimberlites bring up with them, and fortunately enough, they are found before they crushed so that the diamonds are still preserved within them. So just before we start, I just want to acknowledge some of my co-authors. Beth and Richard Kale were really instrumental in collecting this data set, and this was done along with Anton Duplessis, who runs the CT facility at Stellenbosch University. And in particular, I want to acknowledge the late John Gurney. These samples are all out of his private collection. This work was initiated before John passed, and these particular samples were his favorite in the collection, and he was extremely enthusiastic by the results and the data that was collected on these rocks. So I'd really like to acknowledge John in his absence here, and this is probably one of the, if not the last project that he was actually involved in before he passed. So as a titan of the industry, we sort of dedicate this work to him. And so what I'm showing you here is a kind of sneak peek, or before I get into how how the CT scanning works, you can see a little model rotating over here. This is a three-dimensional rendering of one of these xenoliths. And what we've done here is remove the silicates. So the silicates are invisible, and what you see there in gray is diamond, and what you see in red, although not that abundant in this particular rock, is sulfide. So I'll be talking a lot about these three-dimensional models and what we can learn about diamond morphology in the mantle, as well as their relationship to the hosting phases in this case, the source rocks for the diamonds. So just as a little plug before we get on, some of our preliminary or some of the first results were published just a few weeks or just a few months ago in the June edition of Geology. We were also lucky enough to get one of our images selected for the cover. Sorry, I'm clicking on my computer instead of the clicker. Okay, so we were lucky enough to get one of our images selected for the cover here. This is a beautiful octahedra, or a step-faced octahedra poking out the side of one of these xenoliths. And so if you're interested in reading some of the results, you can go and see the June issue of Geology, or send me an email and I can send you a copy of this. So I'll be talking about what we presented in this paper, as well as some of the newer data that we've started looking at since then. So to start off with, why are we actually interested in these rocks? So as we've seen over the last few days, diamonds are predominantly studied as free crystals that are liberated during processing of the kimberlite in the mine. So we lose a huge amount of context of the diamonds when we don't see them within their host rocks. So we all now know, it's well established, diamonds are not crystallized from the kimberlite. They form in the mantle, deep in the mantle, within predominantly peridotite and eclogite, and those that material is entrained by the kimberlite and brought to the surface. A lot of that material is disaggregated on the way to the surface, but some of it survives, and in very rare cases, some diamondiferous fragments survive. And so by looking at these diamondiferous fragments, we can really get context for the diamonds in their host, in their source lithology. And so this sample suite of John's is one of two in the world. The other one is with the late Nick Sobolev in Russia, and so we've done some work on those as well. I worked with Nick in 2015, and we produced some of the similar kind of work then. But really, these kind of rocks are exceptionally rare. And nowadays, with better crushing facilities, they're even surviving even less. So as an appeal to the diamond community and the producers here as well, if you ever find any of these kind of things, we would really love to look at them. And all of these techniques are non-destructive, and it takes about a day to produce one of these scans, so we can look at it, scan it for a day, send it back if you want it, and we can get all these amazing data. But it really would benefit from, obviously, input from the industry. Okay, so the first thing what we're interested in, we really don't have good context for diamonds in their host rock, the textural context. The second important point is that diamonds, when they are liberated from their source rocks during emplacement of the kimberlite, they are not happy in the kimberlite magma. They become resorbed. So when they grow in the mantle, they grow as nice octahedra, predominantly, as well as a few other growth forms. But when they're liberated in the kimberlite magma, they start to become eaten up. They start to become resorbed. And this is in very predictable ways. You go from beautiful octahedras down to dodecs and tetrahedroids. And so we also lose context on diamond morphology because the kimberlite eats the diamonds up on the way up. So what we're interested in is a context, textual information for diamonds in their source rocks, as well as looking at primary diamond morphology unaffected by the kimberlite on its way up. So those are our two primary goals that we looked at in this study. Okay, so what is CT scanning? This is a very common technique in the medical field. Some of you may have gone through this yourself, but essentially it is a way that you can produce images in a non-destructive way of anything from human body parts to rocks. And so a CT scanner looks something like this. And the typical data that's produced are these two-dimensional images. In this case, this is a slice through someone's head where you can see the brain nicely exposed. So this is commonly used in medical practices, and it's now becoming a lot more common in geology as well. So paleontologists use this a lot, archaeologists use this a lot. And if you watched, there was a recent Netflix documentary on the Star Cave where they produced a very nice CT kind of scan using the synchrotron in Europe of some archaeological remains in that case. So a very powerful technique, and the technology is developing very quickly so that the resolution is getting really great. This is not the first time this was done. Dan Schulze did work like this in the mid-90s. At that time, the technique wasn't so good, so the resolution wasn't great. He scanned one xenolith and made some really interesting observations, but now we're starting to see things in a lot more detail, and we can make really great observations and interpretations on what we see. Oops. Okay, so a similar thing can be applied to rocks. This is an example of one of these CT instruments. There's one housed at Stellenbosch University. There's also another one in Somerset West run by a company called Excite, who we're working with now as well. And so we put these little diamondiferous xenoliths. So this is an example. This is about 5 centimeters across. It doesn't have a scale bar in there. And these were collected based on the presence of these little diamonds popping out the edge. These are all eclogite, so you can see the sort of orange-colored garnet and a little bit of CPX in between. And so what we see in the data that comes out, so this is an example of a 2D slice. So you can think of this as more or less of like a thin section which you'd cut through a rock. You cut it, you polish it, and you have a 2D representation of what the rock is, and you can look at the minerals. Eclogites, fortunately, are mineralogically quite simple. There's only 2 major minerals, garnet and anthracite, and they're also quite coarse-grained. So they're really good candidates for doing this kind of work. So here we can see what we're going to see throughout the talk is both 2-dimensional images like this, as well as the 3D models. And what we've got labeled here, the lighter gray is garnet, the darker gray is CPX. The diamonds pop out as these dark, essentially black grains, and then when you get these kind of mottled textures, there's kind of metasomatic modification, which is a little bit finer grained. The sulfides, in this case not very many, but these very bright, almost white spots, those are the sulfides. Okay, so already you can see here the diamonds have these nice, beautiful euhedral morphologies, and we'll talk more about what we see in the data. Okay, so how do we produce these nice images? The X-rays, each mineral has a specific attenuation, and it's essentially based on density. So the other nice thing about eclogites is the minerals have quite different density, so they have different attenuation, and so they show up very well. Diamonds have very low attenuation, so they really pop out quite easily when we see these 2D slices, these dark things. And so here on the x-axis here, I'm showing energy versus attenuation. So this is the mineral's attenuation versus the energy. So you can play with the X-ray energy with the instrument, and based on where you are here, you can see the attenuation of the minerals change. So you really want to be analyzing rocks where you see the greatest difference in the attenuation. The larger the difference in the attenuation between the minerals, the greater the contrast, and so then you can see them a lot easier. So we're fortunate as well for the eclogites. There's a big range in attenuation, so we see the phases stand out quite nicely. And so what we typically do actually, for this data set, we've actually done scans at 2 different voltages and then merged the data sets. Because the attenuation is so different between diamonds and sulfides, it actually oversaturates, so we need to actually do scans at 2 different energies, and then we can merge data sets to get these really nice 2-dimensional slices. Okay, so once we got these slices, typically you get something like 1,000 2-dimensional slices per xenolith. These can be stacked using software, and so what I'm showing you here is essentially a stack of 1,000 images through a xenolith. And so you can see here, we call them flipbooks, so it's like if you put 1,000 images together and just turn the page, you'd get something that looked like this. So here you can see garnet in the light gray, these bright spots are the sulfides, the dark stuff is the CPX, and there you see the diamonds popping up every so often throughout this xenolith. Okay, so you can see them nice euhedral morphologies in this case. As we go through, and what you'll note here as a sort of prelim to what I'm going to say is that the diamonds are never included in the garnets. They're always associated with little, what we call, well, metasomatic pathways through the xenoliths, and I'll show you more detail about that as we go through the talk. Okay, so this is the first kind of data set you can look at. I like to call these things pseudo-thin sections. They're thin sections, but instead of having 1 through a rock, you have 1,000. And so you can get a really great context throughout the whole rock instead of just having one kind of that represents that rock. Okay, and so once we've got this data set together, you can also use, then you can process the data to produce 3-dimensional models. It's come out quite bright there, this one. But essentially, it's fading into color a little bit. Okay, so here on the left-hand side is a picture of the actual diamondiferous xenolith. This one is predominantly garnet, and you can see little diamonds popping out on the edge. And so what we've done here now is produce this 3D model. You can render different phases, invisible or visible. In this case, we've removed garnet, CPX, and everything else, and we've left behind the diamonds and the sulfides. Diamonds in gray, and sulfides, in this case, in red. And so you can also do volume percent calculations. So I think this particular xenolith had something like 9 or 10% diamond by volume. So a huge amount of diamond in this particular xenolith. We're going to come back to this one again a bit later, as it's the best in the sequence, and you can see these beautiful, essentially diamond-filled veins, pathways, metasomatic pathways. And this is what we start to see as a common trend in these. We know that diamonds are secondary, we know they're metasomatic, so this is not necessarily a brand new interpretation, but here we see it in more sort of detail and than anything else, than any time else. What you can also see, and I'll come back to in more detail again, is the diamonds here are predominantly euhedral, but that's not always the case. Okay, so the CT scanning has become an exceptionally powerful technique. We can see really good textures in both the 2D scans, and then we can see the diamond morphology in 3-dimensional, in 3D, in really great detail by stacking these images together. Okay, so let's get into some of the results. So most of the results I'm going to show you today is from our recent work, as well as some of the work we did on some Russian xenoliths from Udashnaya. So like I said earlier, the sample suite is from John Gurney's private collection. I don't know of any other sample suite as good as this. One in Russia, but it's very difficult to get hold of, especially since Nick Sobolev passed away. And so I'm going to appeal again to the audience. If you ever find something like this, we would really love to get the opportunity to scan it. So what we did in this particular study, there were 24 of these diamondiferous xenoliths, and there are a few more in John's collection that we're still going to be scanning. These are predominantly from Newlands and Excelsior. These are group 2 kimberlites, just out west, and 2 xenoliths from Arapa. And so what I'm going to show you is not all of them, but examples of interesting textures and features in a variety of these. And so we'll first look at diamond morphology, then we'll look at diamond silicate textural associations, and then diamond sulfide textural associations. It's important to remember that sulfide inclusions in diamonds are the main way we date them, so it's important to understand the sulfide diamond textural association as well, and we'll talk about that. Okay, so to start with diamond morphology, we saw a range in different diamond morphology within these things, but predominantly the growth form that we observed in these are step-faced octahedras. So these are not your beautiful flat-faced octahedra that you generally see in the pictures. These are called step-faced octahedras. You can see them here, the CT image or the 3D model over here, plus in this case these diamonds that were popping out the edge of the xenoliths. So within all of the xenoliths we see, that all these eclogite xenoliths, the dominant morphology is this step-faced form. And so what does this mean? This is just another 3D model, again showing, you'll see when these diamonds come round, you can see these beautiful step-faced step faces. And what this means, so Jana Fedorchuk, as well as Ingrid Chin, she probably knows a lot more about these than I do, but what they showed looking at diamonds from Arapa, as well as some Canadian examples, when you look at the step-faced diamonds and you slice them and do seal images, so this is an example from Jana's paper a few years ago, a nice step-faced diamond. They slice it open and then do the seal imaging, and you find really complex growth. There's usually some sort of seed or multiple seeds in the center of the diamond, followed by a complex stage of growth and resorption in cases. So when you see these rounded forms, it's probably indicating some sort of resorption. And so they presented this nice little illustration showing the difference between a flat-faced octahedra on the side here, which is relatively simple growth, and then the step-faced octahedras, starting out with multiple nucleation centers and possibly different growth modes, and then going through multiple stages of growth, and then they have these little lines here indicating resorption. So you can have growth, resorption, but essentially it's this sort of aggregated or multiple nucleation centers in the middle that finally produce this kind of step-faced growth. So here we showed really nicely that for this suite, it's all step-faced octahedra, and so it's quite an interesting observation. And so now there are also other forms. When we start to look at the data in more detail, we're seeing partial resorption of the diamonds completely contained within the xenolith. So this is resorption happening in the mantle. And so in this case, what I'm showing you here is a three-dimensional image on the left. You see the beautiful step-faced octahedra pattern on the right-hand side, and then on the left-hand side, you'll see it rotate now in the video. You'll see this big sort of trough, and it's been eaten up on one side. The diamond is unfortunately broken off the surface of the xenolith there, but as this rotates around, you'll see this side, this face of the diamond is completely eaten up. You've lost its kind of step-faced morphology, and as it comes around, you can see that nice euhedral step face again. When we look at this in the 2D images, so on the right-hand side here, you see this nice sharp euhedral side of the diamond. It's basically in contact with the garnet. On the other end of it, you can see this little halo of darker material, which is metasomatic material, and here we're suggesting that the infiltration of fluids or melts along grain boundaries in this case has resulted in this partial destruction, partial resorption of the diamond. So it's not so rare, it's quite rare in this data set to see this, but here's really nice evidence of partial resorption or destruction of diamonds that's occurring in the mantle through melt infiltration along grain boundaries. Okay, in other cases, we see quite strange diamond morphologies. So in this case, in the 3D models here, you see this near spherical diamond. This is the edge that's poking out at the surface, which is exposed here. And then you have the other edge that's completely contained in the diamond. So this is not related to kimberlite resorption. Initially, we thought this might have been a resorption feature, but then it was pointed out by Andy Moore and Steve Haggerty that they resemble quite closely these so-called bullous diamonds, which are a type of fibrous diamond growth. And so we're not quite sure exactly what these diamonds mean yet. If we had a chance to open them up and do seal imaging on it, you would see if it was fibrous or not. But a pretty unusual xenolith, this one. Again, this is one from Arapa. So when you look at the 3D models, the diamonds in the interior, there's a whole lot of them, and they are almost all near spherical. Again, so it's difficult to say exactly what's going on with these diamonds just yet, whether they're a resorption feature, some sort of mantle resorption that's giving these diamonds a kind of rounded shape, or whether this is some sort of unusual fibrous diamond growth. When we look at this same xenolith in more detail, so this is the diamond that pops out the edge. You can't really see it, but pretty ugly. And the 2D images, you see how spherical these diamonds are. But at the same time, we can see examples where you have this near spherical diamond, and then you have a nice euhedral diamond growing right next to it or in contact with each other. I don't know what's happening here just yet, so the plan is to go back to the xenolith and actually do another scan to try and extract that diamond in more detail to see its morphology. So some complexity that we haven't actually figured out yet. Okay, so here's another example of an unusual one in the data set. This is a rutile-bearing eclogite, so the green material you're seeing in the 3D image here is rutile, and you see one sort of diamond aggregate. This is a nice step-faced aggregate of diamonds, and when you look at the 2D images, you can see the grains are all really nice and fresh. There's very little evidence for any kind of metasomatic components, and the diamonds are all in quite sharp contact with the surrounding silicates. So in this case, if we assume that diamonds are metasomatic, they formed in a secondary process, that metasomatic texture is gone, and it's likely that this xenolith has been recrystallized or annealed post-diamond formation so that everything just looks like it's happy together. But this is the only xenolith in the collection that we actually see this, so it's quite rare to see diamonds in contact with silicates. More commonly what we see, so this is one of the examples from Russia actually, this is a Udashnaya one. You can see the 3D images on top, and then the diamonds exposed in these various two-dimensional slices. But more commonly what we see is the diamonds, when they grow, they sort of abut against the garnet, and the garnet actually becomes resorbed. So the diamonds grow at the expense of garnet. So again, this is just good evidence for secondary growth of diamonds. There's some sort of metasomatic fluid or melt coming in. Diamonds are growing at the expense of the surrounding silicates. So they definitely do not form at the same time as the silicate phases. In this case, we also see nice sulfide inclusions even within the diamonds, which is not so common in the more recent data set. So this is just another example. This is the image that I was showing you at the very start of the presentation. These 3D models that we've just shown in various places, nice step-faced diamonds. And when we look at the euhedral diamonds, these nice sharp cut boundaries, you see that, it's difficult to see on this one, but it kind of has a little dogleg there where the diamond is growing into the garnet, so at the expense of the garnet. And they always form in these little metasomatic or mottled pathways, and they almost always have some sort of rim between the diamond and the surrounding silicate where it's this kind of metasomatic material that it's formed from. Okay, so this is the really nice one that I told you about, and this is the one we see the best example for a really well-defined, essentially metasomatic pathway in the xenolith. So the xenolith itself, we saw this one earlier, and I'll show you the 3D model again in a second, but when we look at the 2D slices, we see how many diamonds are within here, and they form very much along this very defined vein. So in this orientation here, and then it comes in again from the base on the right-hand side here. So you have this distinct vein network, and around these diamonds you see all this more mottled material, which is metasomatic material, which probably comprises predominantly CPX, a bit of phlogopite, and some sulfides. And so when you blow that up a little bit, you also see in these cases there's always this little halo around the diamonds where there's been some sort of metasomatic modification of the silicates. So they're not in contact with the silicates. And again, these are step-faced octahedra, so they represent complex growth. It probably didn't grow in one event. This was probably some growth over time, and so these channels probably remain open for some time in the mantle that channels fluids as they pass through these rocks. What you can also see in the xenolith in the red, you have these very distinct little red dots here, the sulfides. They also form in little metasomatic pathways. It's difficult to see here, but these little gray veins cross-cutting here in the 2D host all these little bright spots, which are the sulfides. So in this case, the diamond pathways and the sulfide pathways are completely unrelated. So there's no relation here. Okay, so here's this image again, and this really shows these nice diamond bearing veins, these metasomatic pathways in really nice detail. And this is really good evidence to show that the diamonds are completely unrelated to their host rocks in this case and are forming from these melts or fluids that are moving through the lithospheric mantle. Doesn't seem to be moving. Okay, so that was looking at diamond silicate relationships and morphology, so we're going to quickly look at diamond sulfide relationships as well. And so what I mentioned earlier is that sulfides are our best way to date diamonds, and essentially what we see in this data set is that there's no relationship between diamonds and sulfides. It doesn't have big implications for dating of diamonds because the sulfides, once they're locked in the diamonds, only start their time clock then. So it doesn't matter if the diamond is older or younger. When it captures the diamond, that's when the rhenium osmium isotope system starts. And so In general, we see sulfides that are predating diamonds, post-dating diamonds, and even some that are related to later cracks that are likely during ascent to the surface. So in this case, it's a really nice example seeing, like we saw with the diamonds in the previous one, a very distinct sulfide vein cross-cutting this xenolith. So you can see, again, a high number of diamonds. All of these are, well, they're predominantly step-faced octahedra again, and then you see this diamond vein, the sulfide vein cross-cutting here. When we look at the 2D slices, you can see the bright spots. This is the vein. It kind of just cross-cuts through the garnet, through the CPX, and where we see it coming up next to the diamonds, you get these little bends in this sulfide vein. So we interpret that as the sulfide coming in after the diamond, where it's intersected the diamond has just kind of done a little meander around it. So this diamond, this xenolith is really showing this nicely, this sulfide forming, again, also from metasomatic or secondary processes. As these melts come into the lithospheric mantle, you have these very sulfide-rich fluids or melts that form sulfide, or you have, on the opposite end, the ones bringing carbon into the mantle and forming diamonds, but essentially unrelated to one another. So this is an interesting example. In most cases, we don't see any interaction between the diamonds and the sulfides. This is another xenolith from Arapa. It's difficult to see in this 3D image, but when you look at the diamond on the exterior, it's euhedral, it's got a step face. But when you see the diamond on the inside of the xenolith, it has this kind of unusual morphology, and it's surrounded by the sulfide. And so looking at the 2D images, you start to see the sulfide abut against the diamond, and it produces these, what I interpret as these kind of embayed edges. And so it looks like the sulfide, whatever the sulfur was bringing the sulfur into the lithospheric mantle, when it interacted with the diamond, it also resorbed and partially destroyed this diamond in place. So it's a nice example of some interaction between sulfide and diamond in this case. Okay, and so lastly, we also get sulfides that are very late stage. So in this case, we see the 2D images on the bottom and the 3D at the top and the little rotation. You can see these kind of thin flakes or veins of the sulfide. And in the 2D images, you can see they're related to these late stage cracks that are cross-cutting the eclogites. There's other metasomatic little veins coming through that are completely different orientation. And so these, I think, are late stage, they're cracks, and they've been infilled with sulfide at a much later stage. So there's evidence in these xenoliths for early sulfide, late sulfide, compared to the diamond itself. But essentially, we don't think that there's a relationship between diamond and sulfide formation. Okay, so what have we learned essentially so far? We've learned from this data set, which is still relatively small and only related to eclogites. So what we're really missing is information on peridotitic xenoliths. They're exceptionally rare. I think there's only 1 or 2 diamondiferous peridotite xenoliths that have been reported. And so it'd be really great to get some peridotites as well to see how they compare. In this particular suite, the primary growth form is step-faced octahedra. How representative that is in terms of eclogitic diamonds as a whole, I'm not so sure. Maybe those who have looked at a lot of diamond inclusions, if you see eclogitic garnets or eclogitic CPX in diamonds, are they step-faced diamonds or are they flat-faced diamonds? That would be interesting to get some opinions about that. So in this case, predominantly step-faced. Again, it would be interesting to see in peridotites, are they predominantly flat-faced in the terms of the growth form? I don't know the answer to that. The diamond silicate textural relationship is clearly supporting a secondary origin, a metasomatic origin, which is not a new interpretation. We're just showing it here in really unprecedented detail. And there's also multiple stages of growth and resorption likely indicated here by these step-faced diamonds. And lastly, there's no distinct common link between these diamonds and sulfides. Okay, so what's next? So the plan now is, again, to go back to these xenoliths. You can scan the xenolith, and then what we can do is target individual diamonds within the xenolith. So our hope then is to get every single diamond within the xenolith scanned so we can see the morphology in even greater detail. This is a scan we did a couple of weeks ago by Sarah Burns, one of our colleagues, at Excite, where we took 20 little 1-2 mil diamonds to the CT, and we scanned them to see what kind of detail we could get. And so you can see here there's nice octahedras, there's a couple of dodecs scattered through there. So our plan is now to put these xenoliths in the CT instrument and scan every single diamond to get a morphology that looks like this, so we can see it in even greater detail, especially those ones where we see indications of resorption and things like that. So there's still some work to be done on these. And so to kind of end off with, again, we need more samples, and so I'm appealing to the community here, those that are producing or get to see the diamonds come off the processing plants. If we ever see any of these things, we're really desperate to get more of them. They're completely underrepresented in the literature at the moment. There's a handful of papers that are predominantly done by Larry Taylor, my former postdoc boss in the States, on the Odashnaya ones, and now on these ones from South Africa. So we really need more samples to get a better idea as to how diamonds form in the mantle and give them context, and definitely the prolitic ones. So I'll just leave you with these last two images, and yeah, thanks very much for listening.
Thanks, Jeffrey. Thanks, that was fascinating, and I could follow it. So I hope you get a lot of samples from these guys. I'm sure the guys have taken attention. Okay, any questions? All of them. Yeah. I'm done. Okay, our next presenter is Phil Smith Ndungane. He's a PhD candidate at the University of Cape Town, and he's going to talk about the constraints on the composition of the lithospheric mantle beneath the southern DRC and Angola from major element compositions of kimberlite indicator minerals.
All right, thank you for the introduction. I'm very happy to present this topic today, which is a part of my research. So the title is Constraint on the Composition of the Lithospheric Mantle Beneath the Southern DRC and Angola from Major Element Composition of the Kimberlite Indicator Minerals. So this is my presentation outline. So I'll start with the study area, and also I will answer why choosing the Congo Craton. I will secondly touch the kimberlite field and the respective block. Then I'll do a quick view of the velocity map and methods and sample. Then after I'll go through composition and variation of different blocks based on major elements of the kimberlite indicator mineral. Then I'll do summary and the way forward. So my study area is in the central part of the DRC, of Africa. So it's the Congo Craton. So I'm just looking at the southern part of the Congo Craton, which I'm focusing on the Bangwelu block, the Kasai block in the central part, and the Angolan block in the western part. So why these studies? We know that the chemical and thermal structure of the Congo Craton is poorly known outside the Mbujimai region. So, but we know that the Congo Craton hosts large number of diamantiferous kimberlites. And this study is mostly focusing on the kimberlite indicator mineral because the kimberlite-borne xenoliths are rare. So looking at the kimberlite field and their respective craton, and as you can see from the eastern part, we have the Kundelugu field. The Kundelugu field is sitting on the Bangwelu block, and we have, which is Proterozoic, and we have the Mbujimai field in the central part. It's including the Chibwe, Mulenda, and the Mbujimai kimberlites. We have also the Angolan field where we are focusing on in the Lunda clusters in the northeastern part, and also some data in the central part. We also did some field work in the western part of the Democratic Republic of Congo, where we got the new data from the Kimpango field. So I'm going through the velocity map. As you can see, how it's showing higher velocity, which are associated with the thick craton in the Mbujimai field and Angola, while in the Kundelugu is very low, which is also indicating the thickness, which is also not higher. Looking at the method and sample, so we assembled numerous data from previous researchers, as you can see, and mostly are major and trace elements from kimberlite indicator minerals. So the most kimberlite indicator mineral that we look at it, the garnet, ilmenite, and clinopyroxene of both Angola and the Democratic Republic of Congo. We also have some unpublished data, which we are also working on. After that, we did field work and lab analysis. We also recently got data from the Lukapa diamond, which are from recent field work conducted with the contract of RES. And as we went to the field to do some stream sediments in the uncharacterized clusters, such as the Kimpangu, and we also got data from Matabala and Mulenda in the Democratic Republic of Congo. Then after, we did lab analysis, as you can see, at the University of Cape Town, and we did EPMA at the University of Johannesburg. Assembling all these data, and with our new data, we just combine them, and then we come up with a different diagram to constrain the composition of the lithospheric mantle beneath the southern Congo craton. As you can see from the garnet composition, looking at the on-craton data, you can see it's mostly dominated by lateritic composition in both Angola and the Kasai block. So you must know that these are on-craton. And we also see low chrome, which are eclogitic, are also consistent. Then we saw also the G10 in the Angola and also the G10 in the Congo, the Kasai block. We noticed that in the Kasai block, it's mostly, if you look at it, sort of shifting toward the low calcium oxide, which is more interesting comparing to the Angolan block. So looking at the off-craton data, you can see that it's mostly lateritic, and we have also some eclogitic composition. It's also the same with our new data collected in the Kimpangu. We show the same scenario, so confirming that our off-craton. Discriminating the eclogite composition and the peridotite based on magnesium oxide and chromium oxide, we can see it confirming our previous diagram, which shows it's mostly dominated by periodic composition, and we have also eclogitic composition. It's quite similar between the two blocks, which showing that they are maybe looking like twin blocks. With our off-craton data, we can see also some similarity, but if you look at the Kimpangu with only high magnesium, but in terms of periodic data, they look almost the same. So if we look at now the magnesium number and the titan oxide, we can see that the Angolan garnets are much more megacrystic than the Kasai garnets, but we can still numbers of peridotites, which are also confirming our previous diagram. And then we also did the same thing with the off-craton data. You can see that it's, in the Kundelungu we have periodic dominating, and we also have megacrystic. While in the Kimpangu, it's mostly dominated by megacrystic composition. We did now using low chromium oxide to discriminate the megacrystic and the eclogite composition. We noticed that in the Angolan garnet, it's mostly megacrystic and eclogitic, while in the Kasai block, as you can see, it's dominated by eclogite composition. Looking at the off-craton one, the Kundelugu is showing some similarities with the previous one, but the Kimpangu, it's confirming megacrystic composition. So now, looking at the clinopyroxene composition data, we using the calcium number and the magnesium number, we saw from the calcium number low to higher in the Angolan data. As you can see, from low to higher, we noticed that in the low calcium number, it's associated with a megacrystic composition, and it's clearly showing like a fractional crystallization trend toward the high calcium number. While in the DRC data, we see it's mostly periodic. The trend is still, but not like emphasized in the Angolan data. Also the same, we can see that it's with the Angolan data, you can see a decreasing of the temperature and also fractional crystallization with the eclogite data, while in the high chromium, it's associated with mostly periodic composition. In the DRC data, you can see these data are mostly megacrystic, while this one are periodic composition. Looking at now to compare with the garnet composition, as you can see using the clinopyroxene composition, we noticed that in the Angola it's confirming the abundance of garnet periodic composition, and we also have eclogite and megacrystic occurrence, which is significant. It's the same with the DRC data. We are also having garnet composition and the eclogite megacrystic composition. Then moving in with the ilmenite composition, we use this diagram to discriminate non-kimberlite and kimberlitic field. We can see that in the Angola we have like large data falling in this kimberlitic field, but in this one we still working on it to confirm if it's non-kimberlitic, so it's not typically non-kimberlitic. So that's why we need more information to confirm it. And it's also the same with the DRC data. All are falling in the kimberlitic data beside the Kimpangu, the recent data, that we still have to confirm this data if it's in non-kimberlitic. It's also the same with the magnesium oxide and chromium oxide diagram, where we see a diamond preservation which is associated with high magnesium content, and we have also higher chromium content, chromium oxide, which is also the same with the DRC data. But in the DRC, the difference is you can see that most of the off-craton, because the Kimpangu and the Kundelunga off-craton are sitting in the low chromium content, confirming that could be off-craton, while the Kasai block are showing high chromium oxide. So in summary, we saw similarity between the on-craton kimberlites, the Mujimai, Chibwe, and also the Angolan, which are which are showing abundance of G9 and G10 composition, with also occurrence of clinopyroxene and ilmenite. We also noticed that in the Kundelugu we have rare G10 composition, and then most of our data are showing also some abundance of megacrystic composition. In terms of way forward, we still have a way to go. As you can see, we still have to do some more garnet paragenesis, and we must also do some single thermal barometry of our sample. Then we also have to do some trace element analysis for characterizing our this craton. And also, we have also to do some rare elements for more detail in terms of examination, partial melting, and metasomatism. It will be the same with the clinopyroxene, and we still have to do some further investigation in the ilmenite composition in these studies. Okay, thank you.
Okay, thanks, Will Smith. That was excellent. Can we have the lights, please? Any questions? Okay, I think I'm going to ask that they close those doors because you guys must be smelling the beers because nothing's happening. Okay, I've got a request for Jeffrey. Are you still here? There's a request for a question to you if you don't mind.
All right, thank you. I wanted to ask regarding the CT scan. If you know where your mental nodules come from, maybe where the kimberlite is sampled from, can you use that mental nodule using the CT scan to determine the grade of that kimberlite facie? And the second question is there maybe a handheld machine for CT scan that we can use maybe because it's like handheld XRF? Because, you know, in an underground mine, we normally monitor waste in the drop points we are loading. So there's something that can be convenience and avoiding, you know, doing sampling and all that to determine your waste content. Sorry.
Yeah, thanks. So I'll answer the second part first. No, there's no handheld instrument. They still, you know, this has large instruments, so you need to go to a facility. You can do core. Someone asked me about doing core. You can do core scans as well, if you want to look at stuff like that. In terms of the diamond grade, we're looking at samples that are only, you know, 10 centimeters in size max at this point. You can get grades out of that for sure, but that's not going to tell you the grade of the kimberlite necessarily. That would have been the original material that the kimberlite sampled in the mantle, but most of that material is disaggregated on the way up, so it would release the diamonds. So the diamond grade of these very diamondiferous or diamond-rich pockets in the mantle is very high, but that gets diluted on the way up by all sorts of other things. So you can't really tell the diamond grade of a kimberlite by looking at the xenoliths.
Any more questions for Phil Smith? Oh, there's a question.
Phil, thank you very much. Tell me, are you only looking at kimberlite type 1 or kimberlite and lamporite or type 2, and can you apply both, or can you apply the same plots for both type of kimberlites?
Okay, so if you look at my studies, I'm mostly focusing on the kimberlite indicator minerals. So this will be, then after I will determine if it's which type of kimberlite. So I'm mostly focusing on only kimberlite indicator mineral, not xenolite or the wall rock.
Any more questions?
Okay, thank you.
Okay, the next presenter isn't here, so we're going to move on. The next one is Merli Tau, and he's going to talk about the applicability of olivine geothermometer in diamond exploration.
Good afternoon, everyone. My name is Merli Tau. I'm a PhD student at UCT. My project is, or my presentation is titled Applicability of Aluminium in Olivine in Aluminium in Olivine geothermobarometry in diamond exploration. So geothermobarometry generally involves the use of the chemistry of minerals to estimate the pressure and temperature conditions at which they equilibrate. So in general, geochemical or mineral composition based diamond exploration methods relies or entails determining whether materials in kimberlites contains some materials sampled from the diamond stability field, or whether the chemical composition of minerals in the prospective kimberlite resembles the mineral composition of kimberlites known to contain diamonds. So here we have this model diagram, which is supposed to show a cross-section or a structure of continents or old continental blocks. So here we see the continental root, and then we see the regions where kimberlite melt forms, and we also see this line which indicates the condition or the region where diamond forms. So this kimberlites or this melts that forms here, their destination is the surface of the earth. So they are very energetic, they're very violent. So as they travel to the surface, along the way, they pick up some materials. And these materials, we refer to them as xenocrest or xenoliths. And xenoliths meaning piece of mantle rock, and xenocrest are just single crystals. So my project is based on xenocrest, and these are olivine xenocrest. So basically, kimberlite or Kappa lamprites, which are formerly known as group 2 kimberlites, are the primary sources of diamonds, and their only role here is just to transport diamonds from here to close to the surface so that we can find them. So that's a piece of a kimberlite, the primary source rock with a diamond there. Okay, so traditional exploration methods uses minerals or xenocrest such as garnet, cyanopyroxene, ilmenite, or chromite. So why am I proposing the use of olivine? So the big plus for olivine is that it's very abundant. Like if you look at this, these images which represent thin slices of kimberlite or lamprite rocks under a microscope, we see that all this colorful material here are actually the olivine xenocrest or olivine grains which were picked up by the kimberlites on their way to the surface. So the olivine is much abundant compared to the minerals used in traditional methods. So olivine, because it's abundant, it offers us, or it gives us an opportunity to characterize the sampling depths of kimberlites and also to have sort of a vertical map of the continental route sampled by the kimberlites. Okay, so the mode of occurrence of the olivines. So we have a thin section. So this is basically these under an electron microscope. So we can see that our grains, they have two colors. The dark colors, the dark core and the lighter colored rims. So basically the cores, they represent the grains picked up by the kimberlites, and the rims represent an overgrowth of the grains from the kimberlitic melt. So in general, we have large grains which are generally rounded, and then we also have smaller grains which are angular. And we already talked about the different colors, and the different colors, actually they represent change in composition. So in general, the cores, the composition across the cores is in general uniform, and then there's a jump to the rims, which is a completely different composition. So this project is part, or this work that I'm presenting here is part of a bigger project, but for this presentation, I'm only focusing on 3 localities, and samples used here are from the John Gurney Mental Room housed at UCT. So the locations are Star, which is the number 9, and then we have Roberts Victor, which is 10, and then we have Sandrift, corner here, number 14. We have Finch, 15, and 16, which is Newland. For reference, we are here at Kimberley. Okay. So, and this flow chart, it basically represents a number of filters that I apply to the olivine grains in order to determine whether or not they were derived from the diamond stability field. I will talk more as I go on. So, but the process generally starts here, where I collect a sample, a lamprite sample or kimberlite sample, and then we get a thin, polished thin section, and then we do an in situ major and minor element analysis and laser ablation ICP-MS trace element analysis. Okay. So, as I've mentioned that I apply multiple filters to my grains. We have these diagrams which were developed by Gillian 2018, which is supposed to represent fields, chemical fields corresponding to different mantle xenoliths. So here we have granular peridotites, we have some sheared peridotites, and we have megacrest floating around here. And our main interest are we are more interested on the granular peridotites because those represent, their chemical composition represent the pressure and temperature conditions of mantle or continental roots. So, and also I did some analysis on the rims. We can see that the rims, they basically have a limited phosphorite content, which is basically a magnesium iron ratio. It's restricted here, but there's like a variation in nickel, manganese, and calcium. So I use these diagrams to classify my grains into granular sheared peridotites and megacrest. So we can see here that most of grains, they plot within bounds of the granular peridotite. And then going forward, those that are outside are filtered out. So, okay, this is this data is from Roberts Victor, and then we have data from Finch, and we have data from Newlands, and we can see all of these, they're basically restricted within the fields. And then we also have Sandrift, and we also have Star. And then we have this diagram, which is another filter, a plot of aluminum versus vanadium content of olivine grains. And this diagram was constructed using mantle xenoliths. So, and Busweiler and team 2017, they discovered that the xenoliths, which equilibrated in the spinel field, they plot above this line, and then we have those from the garnet and spinel field plotting at very low aluminum content, and those from the garnet field plotting around here. So here in this diagram we can see that the majority of the grains, they seem to plot in the garnet stability field, which makes sense because the amount of mantle column traversed by the kimberlites, it's mainly the garnet fault, and then a thin slide for representing the spinel field. Okay, now I got to, so here I'm at a stage where I can apply my geothermometer to the grains that that plot around here, because this geothermometer only applies to grains that stabilized in the garnet stability field. So the method, okay, the geothermometer was calibrated by Busweiler 2017. So basically the method is that you combine the geothermometer with the local geotherm of the area of interest. And then from there, you can determine a pressure and temperature conditions at which the olivine grains equilibrated. So this is what I have for Finch. You can see the extent of the olivine grains I have, meaning this is the depth where Finch sampled, and this is, okay, 36, okay. So this corresponds to about 100 kilometers depth and to about 200 kilometers depth. This is what I have for Finch. This is what I have for Roberts Victor. And then we have for Newland and Star and Sandrift. So these diagrams, the PT diagrams, they can only show us that, okay, some of the sampling extends to the diamond stability field, which is this area here, but they don't tell you how much of grains were sampled at each depth range. So here we use this. I plotted the number of grains per depth range. So this is for Finch, a plot of 89 grains, Roberts Victor 66, Newlands 63, and Sandrift 68, and we also have Star here, which is 28. I'll come back there. So on this diagram, we can see that Finch mainly sampled below this yellow line here. Okay, below this yellow line here, and this line is basically the graphite diamond boundary. So most grains were sampled in the diamond stability field. We have like a similar situation at Roberts Victor, and then we have Newlands, which is different. We have like these peaks here above the diamond stability field, and some materials sampled from the diamond stability field. And then we have majority of grains for Sandrift sampled in the diamond stability field. For Star, we don't have many grains that survived the filters, but the grains that survived the filters, we can see that they plot in the diamond stability field. So many Star seems to display, many grains from Star, they seems to display some strange compositions. These compositions, they don't resemble any of the garnet and spinel peridotites. So that's why they were filtered for now. I mean, the project is going on. So I still need to figure out what those grains represent. Okay, moving on. So this is basically a summary of the number of grains analyzed and the number of grains representing equilibrium conditions and the number of grains from garnet facies or garnet stability field, and the number of grains from the diamond stability field, and a ratio between the number of grains from the stability field to the number of grains from the garnet field. So for Finch, we can see that we have 78 grains out of 78 grains derived from the diamond stability field out of 89 grains which equilibrated in the garnet facies. So which is 88% of the grains from Finch, they equilibrated in the diamond stability field, and we have 95% from Roberts Victor. We have 35% for Newlands, 75% for Sandrift, and 93% for Star. And I compare these percentages to the reported grains for each locality. And we see Finch has appreciably high grades, and which is consistent with the high number of grains which were sampled from the diamond stability field. We have the same situation for Roberts Victor, for Star, for Sandrift, and for Star. But for Newlands, which where we have fewer grains sampled from the diamond stability field, this is consistent with the lower grade of diamonds sourced from Newlands Kaffa lamprites or Newland pipes. So one may ask, Sandrift seems to suggest that we're supposed to have more diamonds there. So why are we not having a diamond mine going on there? The information available is that Sandrift was mined in 1905 and 1950s, but the issue there was that the average stone size was too small at that time. So that's why we don't have a mine. I don't know if we have companies revisiting Sandrift at this stage. Okay, now I go on to try and map the mantle, and in olivine there are some elements which are incorporated in terms of temperature, like the incorporation is dependent on temperature. So elements like sodium, calcium, chromium, vanadium. So obviously, if their incorporation is dependent on temperature, and we know that in the mantle, as we go deeper, the temperature increases. This is what we expect. We are seeing basically what we expect. And then we have some elements that do not really depend on temperature. The incorporation doesn't depend on temperature. So we see this effect around 150 kilometers depth. So there seems to be this increasing concentration of cobalt, zinc, and we see the same trend for titanium. And then for phosphorus content, which is basically the ratio of magnesium to iron, it's the opposite trend or the opposite direction, meaning we have a decrease of phosphorus content with depth. Okay, so the general implication of the result is that we seem to see a correlation between the amount of diamond grains, the amount of olivine xenocrest or olivine grains sampled from the diamond stability field relative to the grade of diamonds for each locality. So the result seems to be promising, and meaning we can potentially use olivine xenocrest as evaluator to see if a particular kimberlite or prospective kimberlite or Kaffa lamprite is diamondiferous. And a huge benefit of this method is that it will not require a large sampling program like traditional methods, because olivine is abundant in kimberlite. A setback might be that olivine, which is not so stable at the surface, in many kimberlites, it might be altered. So this method only applies to cases where we can find fresh materials. Okay, and another thing is that there seems to be fertilization of the mantle with depth. I think that's it. And these are some of acknowledgement. Christian, who runs the EPMA lab at UJ, Rihanna, running the ICPMS lab at Stellenbosch. We have a collaborator, Buswaila, and a colleague, Snelletu, and a funder, Simera. We have a GSSA as well. Yeah, thank you.
Thanks, Marilee. That was fascinating. I've got a question for you about sundrift. It falls in one of the mining rights that I own, and as far as I'm aware, the grade is around 10 CPHT. And Gert, I think you mined it at one stage? Where's Gert? Okay. So yeah, it's been mined, and we're not going to go back there, but it doesn't sound right. The information that I had was that and maybe you should speak to Gert. I know they were active there a couple of years ago, and I think that they mined it a bit further as well, and maybe they can give you some more information.
Okay.
Okay. Where did your information come from?
It's from a report from DBS.
Okay.
I couldn't find it.
Okay, but also look around. If I find something, I'll send it on to you. Okay, any more questions?
Yeah, if I can just add, Lyndon, I'd like to ask why did you choose all group 2s, Jeff? Okay, but it's very interestingly, and I don't know if Jock's here, but statistically, if you look at our group 2 kimberlites across the country, and you might know this, they typically, are shown to be more diamondiferous. John might want to comment, compared to all the group 1s. I'd be fascinated to see your group 1 kimberlite data as well. But then secondly, Lyndon commented on it, that kimberlite is right on the Cratton edge. It's a very small fissure, sundrift, and I suspect grade and fissures and dilution go together. So it's the same. Where's Mr. Snyman? Are you here from Newlands? Is he? Didn't he think we're important? We can help solve his problems. Anyway, that is another fissure mine, and it's a pretty tough one. And I think their dilution is also a problem. And then Star's interesting. Just after I left De Beers, I did some work for Derek, who's his name, at Star Mine. And those guys used to count either on a face or collect them in tins, olivines and garnets to correlate the best grade. And I think what you're saying to a point, and great work, is the more heavies and the more concentrate you have, and the more peridotite component, the better the grade. But it's fascinating. So we look forward to seeing the group 1 kimberlites, Jeff. Thank you. And I'm glad you got you must speak to James. Is James here? I'm sure there's some more info on sundrift, because just after I got here, and I think James might have been involved, we De Beers sampled, which you got the report, sundrift. So maybe there's some more info as well.
Yeah, that will greatly help, because I looked and looked. There's very little published information on sundrift.
Yeah. And Star, have you spoken to Jimmy Davidson?
No, I haven't. I'm not in contact with.
Yeah, because Star's also a fisher mine, and Jim, mined all Bellsbank. Obviously, his love at the moment, which is the lamperite, and also mined Star.
All right. Gert sitting at the back there. Maybe you can comment. Gert, sundrift. Didn't you guys test it at one stage? The fisher, kimberlite fisher at sundrift.
Slaap jy?
Not.
Right.
Okay. Any more questions? No. There's one at the back.
Yeah, I just wanted to find out if you've tried to compare that thermobarometry with the Nimis and Taylor 2000. How does it compare? Thanks.
So basically, the geothermometers. So that is on clinopyroxene, right? For now, I'm just using olivine, and then I'm sure as the project progresses, I'm also going to incorporate information from other minerals, such as garnet, the information we are getting from garnet and clinopyroxene, and also other minerals brought up by kimberlites, to see if all this information the minerals tell us they agree. and hopefully they do.
Is that it? Okay, thank you, Mary.
Okay, our next speaker is Sinuletu Ashibi, and she's going to talk about using, she is also a PhD candidate at the University of Cape Town, and she's going to talk about using kimberlite indicator mineral geochemistry to better constrain the thermal and chemical structure and evolution of the lithospheric mantle beneath the western Kaapvaal craton.
And lights out. Hello everyone, I am Sinuletu Ashibi. I'm currently doing my third year PhD at the University of Cape Town, supervised by Associate Professor Fuljani. So my project is using kimberlite indicator mineral geochemistry to better constrain the chemical and thermal structure of the lithospheric mantle beneath the Kaapvaal craton. So I'm basically looking at the greater Buck-Lewis kimberlite cluster. I say greater Buck-Lewis kimberlite cluster because I'm looking at the Buck-Lewis kimberlites, the Finch kimberlites, and the Kimberley kimberlites. So the greater Buck-Lewis cluster is situated near the southwestern margin. So as you can see over there, at this point, oh my goodness, you can see over there. And I'm looking at around 26 group 2 kimberlites and 23 group 1 kimberlites. They are all aged around the Mesozoic era. And as I'm sure most of you know here what a kimberlite is. So they are ultra-basic silica undersaturated, low aluminium and low sodium volcanic rocks that are rich in carbon dioxide and water. So as I've mentioned, I'm looking at kimberlite indicator minerals. So they are mantle-derived minerals that are resistant to secondary alteration at the earth's surface. They include, but not limited to, garnets, clinopyroxenes, ilmenites, and so forth. But I'm mostly interested in garnets and clinopyroxenes, and in this presentation, I'll only look at garnets. So they are used in diamond exploration to predict the diamond grade, to prospect for new diamond mines, and they're also used to predict the diamond potential of kimberlites. And in mental studies, we use them to determine the pressures and temperatures of equilibration and to infer the petrological histories of their source rocks, which is then used to aid in diamond exploration. As Fuljani mentioned earlier, that usually mantle xenoliths are used to study the subcontinental lithospheric mantle, but because not every kimberlite pipe has actually exhumed mantle xenoliths, but almost all kimberlite pipes have exhumed mantle xenocryst, then the question becomes, okay. Can you please go to the next slide? Then the question becomes, could an in-depth investigation of the geochemistry and thermopyrometry of large numbers of kimberlite indicator minerals from a much larger array of kimberlites provide new insights into the composition, the thermal structure, and the evolution of the cratonic lithospheric mantle? Beyond that was provided by mantle xenoliths. Okay, this is going to be a problem. Okay. So the aims and objectives of this project, first things first, was to better constrain the chemical structure and the thermal structure of the subcontinental lithospheric mantle and its evolution during the Mesozoic era. That is why we're looking at just group 2 kimberlites and group 1 kimberlites. And the idea is to use big data statistical approaches, such as mantle transects, similar to what was done by Kobusen in 2008 and 2009. And we also want to use chi-plots. And then after that, we are using more robust quantitative methods of calculating paleogeotherms, that is FETplot. So FETplot is a program that iteratively calculates a paleogeotherm that best fit the PT data that you provided. And after that, so I'm using single mineral thermopyrometry, that the Ryan et al. Thermopyrometer, which is a garnet thermopyrometer, and the clinopyroxene. So another thing is we want to estimate how precise it is in comparison to mantle xenoliths and compare them with one another. And then we want to contrast the chemical and the thermal effects that are associated with group 1 and group 2 kimberlite magmatism. Next slide, please. And so, again, Thank you. So like I've mentioned that we are looking at single minerals, so that means we don't know where they come from. Are they eclogitic, peridotic, and stuff like that? So the first thing is to use a classification scheme to assume their paragenesis. And the classification scheme that I'm using is the Grutter et al. 2004 classification scheme, which classifies the garnets according to their calcium, their chromium, and their magnesium, and their titanium content. So the upper panel over there, that is like all the garnets from the group 2 kimberlites, and the lower panel is the garnets from all the group 1 kimberlites. And you'll notice for the group 2 kimberlites, you have quite a number of G10 garnets, and most of which plot above this line, which is called the GDC line, and then they are high chromium content and they have low calcium content. Whereas most of the G10 garnets from group 2 kimberlites, they tend to straddle the G10 G9 garnet, G10 G9 line, and they are more calcic in comparison to the G10 garnets from the group 2 kimberlites. Just to summarize also what we've noticed from the garnets is that the garnets that are high in chrome content, they tend to be enriched in light rare earth elements, and they are depleted in heavy rare earth elements and high full strength elements. And because of this, they tend to have the S-type rare earth pattern, but not all of them. And then the low chrome garnets, they tend to be enriched in heavy rare earth elements and high full strength elements, and then they're depleted in light rare earth elements. And they're largely calcium saturated, which means that they tend to be more similar to the G9 garnets, whether they're G10 or G9. And then they also, sometimes they show the N-type rare earth patterns. So from now on, I'm only just going to focus on the G10 garnets and the G9 garnets, because these are the garnets that are highly likely to be applicable to the Ryan et al. Thermobarometer, which I'm using. So the single mineral thermobarometer relies on the partitioning of elements between minerals which are assumed to be in equilibrium. So the Ryan et al. Thermobarometer, the nickel in garnet thermometry relies on the partitioning of nickel between garnet and olivine, that it has an assumed nickel concentration. And then the pressure that we're using is the PCR, which is based on the chrome solubility in garnet that is coexisting with orthopyroxene and chrome spinel. Many people don't really like using the Ryan et al. Thermobarometer because of its tendency to underestimate pressures of equilibration when the garnet is not in equilibrium with chrome spinel. Again. So basically, now I'm just going to show you a few PT plots for some of the kimberlite pipes that I'm looking at. At first, right now, you're looking at group 2 kimberlites. So I've picked the Finch. So you have Finch over here, you have Kimberley West, you have Newlands, and you have Bellsbank. So the blue garnets, those are the G10 garnets, and the red garnets, those are the G9 garnets. And you have 2 paleogeotherms over here, which we're estimating using the FIT plot. So basically what we did, we took garnets that had like high chromium content at a given calcium content, and we used those to estimate a paleogeotherm, and then we only, like for G10, and that was the paleogeotherm for G9. And what you'll notice is that the G10 garnets have a tendency to estimate higher pressures of equilibration, and this is all, not just for Finch, but for Kimberley West, for Newlands, and for Bellsbank. And another thing that I want you to notice is that, like, this difference between these 2 paleogeotherms, that is the G10 paleogeotherm and the G9 paleogeotherm, whereas at Newlands, this difference is very small, and at Bellsbank, it's not that small in comparison to Finch and Kimberley West. Another slide. So just to summarize basically what you're looking at, so we define the lab thickness as the point at which the paleogeotherm crosses the isentrope. Unfortunately, you can't really see it here on this figure because I wanted to zoom into the data. Basically, for Finch, the lithospheric thickness that we assumed, we estimated from FIT plot was around about 220 kilometers. And for Newlands and Bellsbank, this is actually very much similar, 215 to and 214, whereas Kimberley West estimate a very thick lithosphere of 236 kilometers. And then if you look at the diamond grade, this is from Sebastian Taub's paper, which was published in 2018. And then the diamond grade for Finch is around about 0.36 carats per 100 ton. For Newlands, that is 0.08, as Mary Lee just mentioned right now. And Bell's Bank is about 0.5. This is actually one of the highest grades for these kimberlites that I will be discussing. And then for Kimberley West, even though it has like this really thick lithosphere, the diamond grade over there is like 0.07, which is quite similar to Newlands. Next slide, please. And then now looking at the group 1 kimberlites, I'm just gonna show you some of the data from Frank Smith. You have Detroitspine, you have Bultfontein, and you have Wesselton. So again, the G10 garnets, they are estimating higher pressures of equilibration compared to the G9 garnets. And so Frank Smith is a really weird kimberlite in a sense that it has an emplacement age that is similar, well, it is exactly the same age as Newlands, but it's not of the same age as like Detroitspine and Bultfontein and Wesselton. And then now looking at the lithospheric thicknesses that is estimated by FIT plot for the G10 paleogeotherm, you see Frank Smith has a very thin lithosphere, 192 kilometers, and the diamond grade is 0.05. And looking at Wesselton, although it's thinner in comparison to Bultfontein and Detroitspine, they all have like really high diamond grades, 0.37, and Bultfontein is 0.54, which is similar to Bell's Bank, and then Detroitspine is 0.32, and these are all just the group 2 kimberlites. Right, next slide. So another thing, so now what we did was to try and filter select the garnets that were highly likely to estimate a representative paleogeotherm. So what we did is something that was done by Gruta et al. 2006, where they picked the garnets that had that had high chromium content at any calcium content, and they basically plotted above the GDC on the first figure that I showed, that calcium chromium content. And those garnets, then when you take those garnets and then you estimate the temperature, and you take those garnets and you plot them on FIT plot, the pressures and temperatures of equilibration of garnets, and you use that to estimate a paleogeotherm associated with them. That is like the black line over here, that is the G10 paleogeotherm. But this is now for all the group 2 kimberlites, and this is all for the group 1 kimberlites. So basically, this is all the garnets that I have from group 2, all the garnets that I have from group 1, where I could estimate the pressures and temperatures of equilibration. Again, the same thing, the G10, they estimate the higher pressures of equilibration. And you notice that there's quite a number of these garnets that plot within the diamond window. Basically, the diamond window is defined as this like point where the geotherm crosses the diamond graphite line, and it also crosses the mantle adiabat. So that is the diamond window over there. And then what is very special about this is that this geotherm for group 2 kimberlites is actually very similar to the group 1 geotherm as well. Can you please go to the next slide? So just in summary of what you're seeing in this figure now is that the group 2 G10 paleogeotherm estimates a lithospheric thickness of around about 223 kilometers. And the G9, unfortunately, I couldn't show the G9 because this figure would have been very busy. So this is now 215 kilometers for the G9 paleogeotherm, which is not very different from this G10 that I'm showing over here. And then for group 1 kimberlites, the lithospheric thickness that this paleogeotherm we have over here, it estimates 212, which is only 3 kilometers thinner than the G9 from the group 2. And then the G9 is also 3 kilometers thinner than the G10 for the group 1 kimberlites. And if you look at the diamond in-depth, which is basically the diamond window, it's quite consistent and they tend to overlap quite a lot. And another interesting thing, so I was also looking at the clinopyrex in thermobarimetry after Nimitz and Taylor 2000. So for clinopyroxenes from group 2 kimberlites, the lithospheric thickness that we got was around about 187 kilometers. We still have to look at that, and we need more data for that actually to see what's going on here. But what's interesting for the group 1 kimberlites, the lithospheric thickness is about 200 kilometers, which is only 9 kilometers thinner than the G9s. And this is very interesting because, you know, the G9 garnets are assumed to be in equilibrium with clinopyroxene, and which means then you would expect these to give you around about the same paleogeotherm estimates, and to give you, like, you know, you expect them to be consistent. And this was very interesting to see them this consistent. And it's also very interesting that we are seeing a very thick lithosphere for group 1 kimberlites, you know. Next slide, please. Oh, sorry, please go back again. No, back to the same, yes. Again. So what I want to highlight again, what you notice in this PT plot, especially at depths greater than 100 kilometers, particularly for the group 1 kimberlites, you see like this high temperatures, this increase in temperatures at relatively no increase in depth, which we notice mostly at here, 120 kilometers. You do see it in group 2 kimberlites as well, but you don't see it as well as you see it over here for the group 1 kimberlites. So what we did now was to like plot depth slices just to try and see what is going on there, looking at metasomatism. Right, again. So now what you're looking at is depth slices between 120 kilometers and 160 kilometers, and a depth slice for 160 kilometers to 200 kilometers. So what you see here is like the average temperature for all the kimberlite pipes, the group 2 kimberlite pipes that I showed you, and the temperatures are well below 1,000 degrees Celsius at that temperature range. And what you notice is this average temperature is quite consistent with what you see in the titanium content of the garnets. What you see, the garnets are very depleted in titanium, but now when you look at the zirconium, it's actually greater than 25 parts per million, which is relatively enriched. So what you see, these group 2 kimberlites are depleted in titanium, but they are quite enriched in zirconium. And obviously, when you look at higher depths now, 160 to 200, you see the temperature is relatively increased, and also you see an increase in titanium, and again an increase in zirconium as well, and also yttrium, but unfortunately I couldn't show that here. But this is, you see that it's only depleted in titanium, and titanium and yttrium, and there's an enrichment in zirconium. Next slide, please. And then now when you're looking at the group 1 garnets, is that you see at every given depth in comparison to the group 1 kimberlites. The group 1 kimberlite, in comparison to the group 2 kimberlites, sorry. The group 1 kimberlites, they show relatively higher temperatures, relatively higher titanium contents, and relatively higher zirconium contents as well. And this is the same thing goes the more you go deeper. As Mary Lee had also mentioned, that you seem to see this increase in enrichment as you go down the mantle column, right? So now, but now what you see in the group 1 kimberlites is that you have enrichment in titanium, zirconium, and yttrium. Again, I couldn't show that. So this is consistent with what was observed by Kobus and et al. 2008 and 2009, which suggests that these garnets were affected by different styles of metasomatism, the group 2 and the group 1 garnets. Right. Okay, next slide again. Okay, so basically what we're seeing now is that, what we've seen is that the garnets from group 2 kimberlites, they tended to estimate a thicker lithospheric mantle in comparison to the group 1 garnets. And I mean, from that you would expect these group 2 kimberlites to estimate, to yield higher diamond grades, but actually what we noticed is that, especially for Newlands, is that you have these low diamond grades. Whereas the group 1 derived paleogeotherms, they calculated slightly thinner subcontinental lithospheric thicknesses, but then the grades are higher, especially for the garnets from the Kimberley, from Kimberley, that is Bultfontein, Wesselton, and Dutoitspan. And another thing that I noticed was that the paleogeotherm, the group 1 paleogeotherms, whether it's G10 or G9, they tend to be quite similar to the G9 paleogeotherm for group 2 kimberlites. It's almost as if they're all related in some sort of way. And then another thing that we noticed was that when I carefully picked the garnets that are highly likely to have been in equilibrium with chrome spinel, now the estimates of the paleogeotherms for both group 1 and both group 2 were quite consistent with mental derived and clinopyroxene derived paleogeotherms. And then, but still, even though the group 2 and the group 1 paleogeotherms were quite similar, you could still see that the G10 paleogeotherms are a little bit distinct from the other three, which is the G10, the G9, the G10 and G9 from group 2 kimberlites, and the G9 from group 1 paleogeotherms, which shows that there is evidence of a thermally perturbed paleogeotherm, which seems to be most evident when you're looking at the group 1 group 1 paleogeotherms than when you're looking at group 2, which almost now seems as if the group 2 SLM was not affected by metasomatism, or it looks like it was not heated up by metasomatism. Right, another slide. So just to basically summarize this, it looks like between 200 to 114 million years, the SLM interacted with potassium and water-rich melt, which then which when you look at the garnets, what you see is the enrichment in zirconium, in light rare earth elements, and calcium enrichment as well. And because of the depletion in these garnets, because of the depletion in titanium content of these garnets, it is suggestive that these garnets were actually in equilibrium with phlogopite. And now, when you're looking at the temperatures, it appears as if, because like the fact that you see the G9 garnets to be warmer, it's suggesting of like incipient heating. And when you look at, then at 112 to 186 million years, there appears to be this like pervasive, the SLM interacted with carbon dioxide rich silicate melt, which was more pervasive at metasomatizing the SLM, and then this is now shown by the enrichment in light rare earth elements, in calcium, titanium, zirconium, and yttrium enrichment, and this is what Kobusen refers to as the clinopyroxene generating metasomatic event. And what we also noticed is that the G10 and the G9 paleogeotherms for group 2 kimberlites, they tend to be quite similar to one another, which is suggestive of like thermal equilibration between the two. And it also appears like that heat was distributed more effectively by these group 1 kimberlite melts, group 1 kimberlite related melts. And now what we noticed is that the extent of metasomatism appears to be largely governed by the metasomatizing agent. If you have a hydrous-rich melt, metasomatism is not readily observed, whereas when you have like this carbon dioxide-rich silicate melt, then it appears that the SLM has been pervasively metasomatized. And to quote Nimis et al. 2020, especially for the Kimberley kimberlites, it appears that the group 1 related metasomatism was diamond friendly, even though it was more pervasive. I mean, this is open for discussion. So in conclusion, I'm almost done. So in conclusion, we propose that heating of the subcontinental lithospheric mantle started immediately prior to the onset of group 2 kimberlite magmatism. Right. And then the similarities between the group 1 G10 and G9 with group 2 G9 paleogeotherm is indicative of effects heating associated with the Mesozoic era metasomatism, and it is because of the metasomatizing agent that the thermal effects are less pronounced in garnets that were exhumed by group 2 kimberlites. Right. And then also, the subcontinental lithospheric mantle between group 1, beneath group 1 kimberlites has been more thermally perturbed as a result of metasomatism by the more effective group 1 related kimberlitic melts. And now, after thorough picking of the garnets that were likely to be in equilibrium with chrome spinel, it appears that we can actually calculate a steady state, calculate a geotherm that is more representative of steady state, that is devoid of transient thermal perturbation. Right. Thank you.
Thanks, Senator. Any questions? Okay, one at the back.
So, two problems. I'm partially deaf. So I don't think I actually understood your question very well. But I will try to answer, and then if it's not what you wanted, you can just tell me. So firstly, we are not really interested at the number of like how thick the lithosphere is, basically just like how to, because like as you mentioned that there is like an uncertainty which is associated with the diamond in window. What I was really interested in mostly is like the diamond in depth, because that seems to not fluctuate quite a lot, whereas the lithospheric thickness seems to be fluctuating quite a lot. And that is also very associated with the garnets, I mean, if you have selected something that has been affected by metasomatism, that tends to fluctuate a lot. But now, if you see similarities between the diamond in depths, then that is where you actually like, okay, this is good, you know, because the diamond in depth is the one that will tell you that okay, you're right, basically, but not the lithospheric thickness is a bit shaky.
Yeah, so basically I was just curious about what the uncertainty on your lithospheric thicknesses were.
So,
because for some kimberlites, you have a difference of 20 kilometers, and I was wondering if that was resolvable from the uncertainties on the geotherm.
So basically, I'm not quite sure what the uncertainty is there, but what we're doing is using the uncertainty that is provided by the diamond in depth as the uncertainty for the lithospheric thickness.
Okay, thank you.
Right.
Lyndon, if I can just ask, I mean, these kimberlites you're talking about sort of immediately precede the Karoo volcanism.
Some of them.
Dokalwaya was 2005, or 205 million years, and Joneng is 240. And then, a lot of ones that, most of the ones you're talking about are post-Karoo, 188 million years. So what possibility that massive outpouring and obviously mantle effects helped some of that metasomatism? Have you thought about it yet?
No, not the Karoo bus. We have not really thought about that, but we have thought about like about how the group 2 kimberlite magmatism may have come. I have looked at the possibility that was suggested that there was a mantle plume that led to the opening of the Indian Ocean and the Atlantic Ocean, but I have not really looked into the Karoo basals themselves.
Yeah, just a thought, but
right.
More discussion.
Right.
Thank you. Very slick presentation, but with all due respect, if I may point out a possible typing error.
Yes.
And it'll make our minds look so much better if you get it right. The grade that you quoted in your charts are carats per ton, not carats per 100 ton.
Oh, okay. Sorry.
Your presentation will look better with much higher grade in it as well. Thank you.
Thank you for that correction.
You can blame your supervisor for not checking your presentation.
Well, I changed it last minute, so it's on me. Thank you.
Okay, that brings us to the end of our program. I think it was a very, very successful symposium. Firstly, I'd like to thank all the presenters. I think the quality of the presentations were brilliant. I think the topics that were covered were very relevant to what's happening in the industry at the moment. It's great that we had so many students here. As you saw, many of the presenters are on the wrong side of 50, and we need you to come in and take over the reins. It's really a big concern to those of us that have been in the industry for a long time that the transfer of knowledge from old to young is not taking place efficiently enough. When I started working for De Beers more than 30 years ago, they had an excellent training program, and we had the likes of Jock and John and Herman Grutte, Mike Skinner, George Reed, all those guys around that gave us long lectures and spent a lot of time with us. And that gave us the confidence to start out our careers as diamond geologists. Most of those geos are not working for De Beers anymore, but they play a pivotal role in many of the other companies in the diamond business. Symposiums like this, as well as the diamond course that some of us are involved with, are crucial to fill the gap in this transfer of knowledge. The biggest issue on everybody's mind is still the state of the industry and what we can expect in the next 6 months, year, 10 years, and even beyond. We were fortunate to have the expertise of Paul and Avi and Peter and the likes who were confident that the current slump in prices in certain categories were temporary due to the economic situations in America and China. The market for natural diamonds and lab-grown diamonds should eventually diverge naturally and as lab-grown diamonds become cheaper and cheaper. The more research-orientated talks of this afternoon were excellent and once again showed why the kimberlite-related research of South African universities are so highly regarded. And I really want to compliment the students. I really thought all of you spoke very well and you presented your data really, really well, and it was well done. Locally, the news is not so good. The biggest threat to the junior mining industry is still the state's inability to properly manage the mineral resources of South Africa. Corruption and the paucity of skilled personnel at all the regulating authorities is delaying the speedy processing of permits, which is crucial to our industry. The future of inclusive mining in South Africa is dependent on the creation of a strong and vibrant junior mining sector, driven by an investor-friendly regulatory framework. This is also key to job creation and the upliftment of local communities. The main social responsibility of junior miners should be the creation of jobs and to pay taxes. The government's responsibility should be to spend these taxes widely on infrastructure and upliftment projects, which will create even more jobs. We have some of the most promising geological settings in the world for the discovery of minerals, but the skill set at government level to unlock this enormous potential is absent. We need to move away from the populistic policies and start to address the real issues hampering the exploration and mining of the abundant resources that we have. The fact that we had no representation from the DMRE at this, one of the Kimberley Showcase geological events, is indicative of government's lack of understanding of the importance of the minerals industry. Our saving grace is that, as we saw during the past 2 days, we still have many people that are passionate about the industry and are not prepared to allow the industry to be destroyed by government corruption and incompetence. From SATPO's side, I can assure you that we will not stop plugging away at all the issues that negatively impact our industry. Our goal is that the resources of South Africa should be made more easily accessible to everyone in order to create jobs for as many people as possible, especially the rural areas. Of course, none of this would have been possible without our sponsors. Normally, when organizing an event like this, and especially in these difficult economic times, the finding of sponsors is the most difficult task, and I can honestly say at this time, it was the easiest task. We really have a bunch of sponsors that understand our industry and were very supportive. And I would like to encourage everyone to please support all of them, as they are the ones who truly have the best interest of our industry at heart. Many of the smaller suppliers that you see on the list are the unsung heroes of our industry. And if it wasn't for their understanding of the industry and the way that they do business with us, I promise you this industry of ours would be a lot smaller. Last but not least, I would like to thank my fellow committee members. The symposium would not have been possible without a team of people that worked very hard to organize everything. Tanya, Rosalind, Gert, John, Jock, thank you for your time and your effort.